Okay, hopefully I'm going live. I should be live. You won't be seeing me, you'll just see your chats up there. I'm just checking to make sure we have no echo. Yeah, I got to make sure that does not play. Okay. And hopefully you guys can hear. And hopefully in a moment you will see. So here I am. Hello, hello. Hopefully you guys can hear me and see me, and there is no echo. No echo. I think I have it licked. You know, third time's a charm, right? I've done it. I've gotten echoes twice, but let's see if, good, no echo, and it's not building. Excellent. Okay. Whew. Have to get used to this newfangled stuff. All right. Hi, all. Excellent. I'm glad you guys can hear me, and I'm not quiet, right? I've got the levels up loud enough you can hear. YouTube is horrible when it comes to levels, so hopefully everyone's good, and I don't sound distorted either. Okay. Lovely. So hello, everyone. Thank you for coming to this space weather, this long series. I mean, we're at the fourth one in this series now. Analyses of extreme space weather events. I didn't have extreme up here, but today we are definitely talking about extreme events. As a matter of fact, we're going to be wrapping up. I was hoping to get done talking about extreme events with this one, but it looks like we're going to have one more. And it's not so much because we need to continue going over Carrington class events, although there are a ton of Carrington class events that we could still talk about. Strangely enough, a lot of people don't know that there have been quite a few different Carrington class events in our history, in our near, almost modern history. But we need to kind of transition into more of the modern day, the space age, more of those events, and talk about them. So that's what I'm going to be talking about at the end. But I wanted to make sure that everybody got to come online, and we get to make sure that my sound is still good. I see George, Secret Owl. I see Big Blue Rock and Lynette. Thank you, guys. I see Chris. Thank you for joining. I love it. And if you see Mike Richardson, he is the moderator today. We may have Jerry on too if he gets a chance, but most likely we're going to have Mike Richardson taking care of things today. So if you see him, please give him a big thank you and a big props, because he will take care of you. He will keep things on topic. And if you don't see, if I don't respond to any questions you might have as the process goes on, when I start going into the Q&As, he will elevate your question, because anytime he posts something or Jerry posts something, I see it and I obey, and it gets my attention right away. So keep posting questions. If you don't get yours answered, don't worry if you feel like a broken record. I'll eventually see it, or like I said, ask one of the moderators to elevate your question. Also, for those of you on Patreon, if you prefer, definitely feel free to use the Patreon comment section to post questions if you don't feel like you're being visible enough in the YouTube chat. I can completely understand sometimes it gets a bit overwhelming. So hello, everybody. Excellent. Thanks, Mike. I appreciate you pinging you and let everybody know that you're here. You can tell Mike Richardson, he's got the little wrench right by his name to let you know he's the moderator, and he will take care of you. Okay, and hi from Brazil. My goodness, love it. I love that we're got tons of people all over the place. Okay, yeah, hooray for Mike Richardson. Okay, so, and thank you, Steffi B, for saying many thanks to the patrons for making this all possible. Yes, and I'm going to go into that in just a moment. I'm now going to take, I'm now going to take off all of your chats, which I see here. I'm going to take them all off so I can put everybody on Patreon who has done such a wonderful job sticking with us. Some of them have been with me for years and years, and they're the reason why I'm able to do these. And it's really, really fun, as you'll see today. I've taken a ton of time putting all of these charts together. I've done some pretty serious research because it gets hard when you start talking about events from the way past, when there's not a lot of records, and then also trying to put this stuff into perspective. Those types of charts take a long time too. So hopefully you enjoy today, because you should walk away with some really thoughtful concepts, thoughtful feelings and maybe some excitement for the next class, which is really going to tie all of it all together with some of the more modern events. Okay, let me change my screen here so that I take your chats off. Don't worry, the chats will still be there. You're just not going to be displayed on the screen. I can still see your chats. I probably can't read them very well, so sadly, because I've got them offline. And I will, what I'll do is that when it goes to Q&A, I'll go back and put the chats up so that we can see better. Okay, so as always, this course has been brought to you by so many unbelievably generous people. All the patrons here, all the mini course patrons, these are all the wonderful folks who have, decided that they wanted to support what I do and make these courses completely possible. They also are the ones that give me the green light, the thumbs up as to whether or not the courses that I suggest or the material that I suggest that I'm going to do in these courses is right on target or way off. And there are definitely some who have, I have a long list of things that that people want me to talk about. So Carrington events were, of course, were a biggie. So that's why I'm doing all of this, and I'm doing so many deep dives. But thank you to all of these people. If you don't see your name here and you are one of my mini course patrons, just ping me in Patreon and I'll correct that right away. Okay. And then of course thank you to my VIP steering committee as well as my Radiant Star and one-on-one patrons. You guys are you make everything tick, and you give me hope that what I'm doing is the right thing and going in the right direction. These are the people that steer the ship. All of these people, and I have private conversations with them, and we get together in a steering committee as well and talk about different things. And we've actually had breakout groups now with some of the different things like heliobiology, and now our super communities. We're going to start doing breakout groups there as well, because there's just so much we want to cover and so many ways we want to serve the community, and the community has just a vast number of needs. So I think right now my VIP list is full. The steering committee is full, but if you are someone who's been waiting patiently to become a steering committee member, just again ping me on Patreon. And we'll chat about it, and we'll see whether or not I can find room. It is a very active family in that sense. We all know each other very well, and we appreciate all of each other's input. So it's like I said, it's a wonderful community, and these guys are really the ones that help kind of not only get me to fly straight, but also make sure that I'm absolutely answering the community's needs as they see fit. And then of course on Patreon, if you want some basic stuff, you can just join Patreon without even worrying about paying. Don't worry about that. I mean, there are people that just follow, and you get a lot of good stuff there as well, because I do a lot of stuff, just early alerts for different things that are coming out, and everybody here is incredibly generous in the sense that they want the community to be a tight-knit community, and so we all respect each other there. Okay, so without any further ado, I will wait to ask questions. What I'll do is this time I'll stop in different sections and take questions, and I'll pull your comments up, because right now I can't see them. They're all kind of like really small in a corner on one of my screens, so I can't read them, sadly. So if it seems like I'm ignoring you, I promise I'm not. It's just that I can't read your comments right now. Okay. So what we're going to do in this particular one, I'll take a tiny bit of time to review. I don't have a lot of time to review, and the reason for that is because there's so many charts because I'm going to go over 2 different Carrington class events this time. I'm being blinded by my light here. I have 2 different Carrington class events this time that I want to talk about. And so I'm only going to give you a tiny bit of a review of just the basic Carrington stuff that's kind of been the architecture of this whole series, this A series. And then I'll talk a tiny bit about the 1967 event, which nearly got us into a world war. That was a fun one. So if you want to see that one, go back to A3 and you will see that class. If you want to go and see the 1972 event, which I talked about in A2, watch that one. That was really what I call the Apollo storm. That was really interesting as well. And then of course, if you want to see the classic Carrington event and all the analysis behind that, go to A1 in this series. Okay, in the analysis series, the A series. All right. So you guys are probably getting sick of seeing this slide if you've watched all of them. But this is a slide that really kind of sets the stage for what we try to define, or what we want to define as a Carrington class event. We have so many myths and frightening, fear-mongering, scaremongering tactics that are used when it comes to Carrington class events. It's not even funny, right? Things like names like mega flare and kill shot, micronova, power grid killer, Armageddon from the sun. I mean, it becomes a religion at some point, right, with God's wrath, and anything that is spelling doomsday, especially when it comes to our Earth's changing magnetic field. I can't even call it a flipping magnetic field because geophysicists don't even know if it is flipping. We've had many excursions like this where the magnetic field strength of the dipole component dips and weakens like this and then comes back. So they're not even convinced yet that that our field is flipping, because historically, it doesn't always have to happen. But it is changing, so I'll call it a changing magnetic field. And because it's weakening right now, you know, people think that, oh my goodness, if we have a Carrington class event, it's going to be the end of all humanity. And it just doesn't work like that. Space, remember, it is just weather. So even a really bad event, we have ridden through them in the past, and we will do so again. And, you know, there's lots of colorful pictures, right, with like, you know, power lines arcing and sparking and lighting on fire, and, you know, the sun like doing some type of bizarre, you know, fireball laser on the Earth and just frying us, right? People drawing pictures of aurora that looks more like flames than what actual aurora looks like, and not knowing that this isn't fire. You'll see in the events that we talk about how many people look at the sky and thought that something was on fire. And, you know, even people who try to show this as an actual event where you've got some magnetic shield standing this stuff off, it still looks frightening, like as if we had this massive, you know, literally massive amount of stuff coming at us, and it's really not as massive as one might think. And it's just because it's so large. It's, you know, the Earth only penetrates a very tiny part of it. So people say, well, these big Carrington events and these big CMEs are, you know, they're many times the mass of Mount Everest being thrown at us. And it's like, well, yeah, the CME itself is that big, but Earth pokes a hole through it like a pinhole, right? And so it's only a tiny fraction of that we actually ends up being impinging on Earth. It's not, you know, it's not the end of the world, and it just can't be. I mean, our atmosphere is more dense than the stuff that the space environment can throw at us. So seeing this kind of thing just drives me nuts. Anyway, okay, so yes, no to all of this back here, right? So this is kind of what we were moving toward, was that you can't define, it's not quantitative to define things in terms of mythology. You have to define things in terms from a scientific perspective, right? So how do we define it? We've gone over this so many times now. By eruptive signatures, right? Coronal mass ejections being launched out of the sun, right? And for those, again, who's this may be the first time you've joined one of my mini courses, please know this is to some degree an advanced class. So I will be using these acronyms and things quite frequently. I'll try to stop and qualify them, but if you don't know what a coronal mass ejection is, I do have the C series of courses, and you can take a look, and it starts with people having absolutely no knowledge whatsoever of space weather, and that's a great place to start. So you can take a look at the C courses, and you'll learn all about coronal mass ejections and ICMEs as well. And then you can work forward and you can learn about solar flares and radiation storms and all sorts of things. So this is kind of putting all of that together, okay? So please, if you feel lost, don't worry. There is material out there that will help you. Because this, like I said, this course is kind of putting it all together so we can analyze these really big structures. So when we talk about eruptive signatures, we're talking about coronal mass ejections, these big solar storms that come out and cause aurora, you know, the stuff that they're trying to say this is. Or do we do it by solar flare signatures? And those are the paparazzi bulbs on the sun, right? They go pop, 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 and the beautiful lights and stuff like that, but then cause radio blackouts. You can, you know, that's what everybody gets scared about and says the X-class flare, right? That's a flare. That's not a CME. These two things are separate. So could we quantify it by those? Well, sometimes. Can we qualify it by the particulate, the radiation signatures, the solar energetic particle events, you know, or AKA radiation storms? Well, sure, we can do that as well. But all of these things are separate phenomena, and not all of them, just because one is big doesn't mean this is big. And if this is big doesn't mean this is big. I mean, it's just, it can be all over the map. And then, of course, you have to actually have effects at Earth, right? Because effects at Earth are completely different than the phenomena at the sun. For those who have taken both the basic series that talks about the solar phenomena and then have taken the advanced series of the effects at Earth, know that there's two chefs in the kitchen. You've got the sun throwing eggs at us, right, at Earth, and then you've got the second chef, because the sun is the first chef, and then you've got the second chef that catches those eggs that the sun throws and cracks them into a near-Earth skillet and scrambles them up. And that second chef is just as important as the first one, because the first one can send us these eggs all the time, and as big eggs as it wants. But if those eggs, those phenomena, are not organized in the right way, then they really don't cause much of a problem at Earth. The second chef just grabs them and say, and tosses them away, instead of scrambling them up and throwing them down at the planet. So you have to really take a look at Carrington-class events and these massive events according to a lot of different, independent in many ways, or at least reasonably independent, measures of intensity, okay? And effects at Earth is a big one. So when it comes down to it, it turns out that defining Carrington-class events is quite tricky, right? Very tricky. And it doesn't mean that just because you see an X-class flare or a X32 that you're going to get an incredibly intense Carrington-class event at Earth. May not be that at all. So we went into, in the first class, we went into this paper, and full disclaimer, Chris Russell is my lead author here, is my thesis, was my thesis advisor 100 years ago, and sorry, Chris, and Janet Lumen is a good friend of mine, and I also know Pete. So I know all three of these authors, and they're very savvy, and they did a really great job talking about Carrington-class events, and kind of, not because the scientific community really needed a lesson on the difference between mythology and science, but rather really trying to understand, with all these different quantitative signatures that we have, how do we classify Carrington events, because it's kind of squishy. So we talked about this in A1 very, very, very much in depth, and this is one of the main plots that we pulled out of the paper. And really what it was talking about was kind of the observer angle, the angle at which, if you're seeing an event on the sun, happening on the sun, where is that relative to Earth? Is it on the east limb? Is it on the west limb? Is it right dead center? Because that then dictates whether or not you have a big flare. You might have an X-class flare, but if the coronal mass ejection or solar storm is shot that way, well, it's not going to hit Earth. So is it a Carrington-class event? Not at Earth, right? Doesn't matter if it could be an X50 class flare. You can't say it's going to be a Carrington-class event from that, because the CME is an unknown and it goes off in some different direction, right? So that's a perfect example of why you can't use flare classifications to dictate whether or not you actually have a Carrington-class event. And then, of course, speed, and they're talking about here, this is what they really were talking about, was speed relative to observer flare angle. When we talk about speed in this case, they were talking about the speed at which, when it hit Earth, and how to back out the direction that the CME was going, how that affects the actual transit time to the distance, basically Earth's orbit, whether Earth was in the path of it or not. And so they had to basically kind of correct for flare angle, because a CME that is aimed directly at you is going to reach you faster than a CME that was aimed over here, and then the flank of it hits you. Let's say my elbow hits you, if that's the flank of the structure moving out. So this side, the side of a CME, takes longer to hit you. So you have to kind of go back and say, okay, well, how far off axis was that thing fired? And therefore, how much longer would it have taken based just on geometry? And that's kind of what these guys were working out here. But what's neat is that you see a bunch of little events kind of scattered all over. And I won't go into the details of it. You can go back to A1 for that. But here's our beautiful 1859 event, okay, back in September. And it had, I think it was, the transit time as they looked at it was what, 17 hours, that's right, 17 hours to reach Earth, essentially, okay? So that was pretty big, right? That's our benchmark. But notice, it's not the fastest, right? When we went through the 1972 event, that was actually the fastest. That reached Earth in just under, or just over 14 hours. So believe it or not, the Carrington-class event the famous one, right? The one that some people think is the only one that has ever hit us, right? That is not actually the case. Okay. Now, 1972, this was the Apollo event, the Apollo era event. This is the solar storm that, when it hit us, it was in between two different Apollo missions, right? And this had a massive radiation storm associated with it. So it was pretty dicey. And there are some impacts that, if you go watch that class, which like I said was A2, we talked about how lucky Apollo astronauts were. Okay, so we went into that in pretty intense detail. But the storm itself wasn't all that strong. It was the radiation storm in that particular event that was super strong. And now we're going to talk about this one. Okay, September, this will be one of the two that we talk about today. In fact, do we have the other one on here? Look for 1921. Nope. And that's probably, and that's got to be right, because the 1921 event, I think it took 20 and a half hours, something like that. We'll find out. I've got so much data running in my head, I can't remember, I can't keep the two straight. But we have this one. This one was the playoff storm. We'll talk about this. And this thing had a massive geomagnetic storm. And then we'll also talk about the what is it, May of 1921, and that is the railway storm. So both of the storms that we're going to talk about today were not the fastest to hit Earth. Okay, so only one of them, in fact, do they classify on here as a Carrington class event. And it may be because the May 1921 storm, they had a hard time classifying it because there just wasn't that much data back in 1921. We didn't really know when the flare hit. I'm not sure we even had a magnetic crochet that we could talk about. It may not have been caught. So just because it's not on this list or this diagram doesn't necessarily mean it wasn't a Carrington class event. It just means that they couldn't analyze it on, there just wasn't enough data for it. And yeah, I'm looking again to see. I should probably, if you guys give me just a sec, I will put your comments back up here, because I'm not going to put it on the screen, but I'm going to put it up here where I can read them. Because sometimes you guys have some really good comments. Like you see stuff on the charts that I miss, crazy poop like that. And I really need to make sure that, that I see what you're saying. Okay, whoops, hang on. Give me 1 second. Put this here, and I'll put this here. Okay, so now I can see you much better. I like being able to see you guys talking, especially if something goes wrong. You guys can tell me. Okay, so the difference with what we're going to, well, I'll go ahead and review. What I'm going to go ahead and do is I'll go ahead and review the 1967 event very briefly, okay? Again, if you want to see the details of that one was fun because it was like, oh my gosh, we almost got in a nuclear war, as you'll see here in a minute. But if you want to see the details of that, that was a pretty crazy one. Oh, I guess do I really need to do this? I don't really need to do this. This is stuff we've done before. Let me skip through this, because I want to get through the time. All right. So May 1967 event, the war in USA narrowly avoided, right? And again, I'm just talking about a little bit of what's going on. Just to give you kind of a reminder, okay? And I might mention a few things about the 72 event just to kind of refresh your memory, because it's going to matter at the end of the class. So back in 1967, we did have eyes on the sun, and we were able to take photographs. And we had this really ugly sunspot cluster. As you can see the dark spots here. And this region, as it went across the disk, we actually did see some white light flares from this region. As a matter of fact, there were multiple flares from this region that occurred. And let me see if I can show it. So you can see, here's a diagram from this particular paper where you can actually see the white light ribbons, okay? And if you recall from the 1859 event, that was how Richard Carrington originally saw the actual flare, was that he actually was the first one to ever draw these white light ribbons from a ground-based telescope, right? Because most of the time, we don't see white light flares. They have to be really energetic to see white light flares, because most of the time the emission of flares is at a much higher frequency, right? Much higher energy of light. And so our atmosphere shields all that out, right? This is why we can't see the extreme ultraviolet, the fun stuff that we see in space-based telescopes. We don't see that on the ground. And that's why some people say, oh, it's CGI. They're just faking it. Those scientists, they just lie to us all the time. No, it's actually, thank God for it, it's our actual atmosphere that absorbs all of that X-ray and extreme ultraviolet light. Thank goodness for that, because if the sun didn't, if the atmosphere didn't do that, we'd all be fried. We wouldn't be alive. So that's why astronauts have to have extreme protection when they go out into space. Their sun visors and stuff have to be able to shield out all that, or it would cook us, because that energy is just so incredibly intense. And so we're not able to see the hottest parts of the sun at least the near surface of the sun, near the chromosphere and then the corona. We can't see that stuff from the ground because our atmosphere is shielding that out. And so our sun looks reasonably bland on the ground, right? It's just a big yellow ball with black spots on it. But sometimes when there's a solar flare occurring, the flare is so intense that not only does it give you X-ray emission and then extreme ultraviolet emission, but it emits clear down into the visible. And that's when we see these ribbons that are white light. Of course, if you were looked at the ribbons in EUV and X-ray, you'd see them too. They'd just be longer and bigger and more intense. And then you'd see all sorts of other things like post-eruptive arcades and lots of fun stuff that you can't see on the ground. But in this case, we saw a white light flare on the ground. We saw multiple white light flares, actually. And that's when you know that this sunspot cluster is not messing around. It's serious, and it's going to be launching something pretty intense. And when they took actually pictures, this was H-alpha, I believe, H-alpha images over a period of time, and you can see here from 1838 UT to, let's see, 1838 to 18, why does it say 1829? When do I write 1838 first? Oh, sorry, that was the other picture. Look at this set of 6, my fault. 1829, 1840, 1844, 1844 a little bit later, 5 seconds later, 1844, or 15 seconds, 1844, 50. So you're seeing quiet time, but you're seeing it begin to light up at 1840 and 50 seconds. And then by 1844, 4 minutes later, the whole area is lit in H-alpha. It's just a big mess because the whole thing has been engulfed in this flare, and is glowing. So we've got lots of loops and things reforming. So it was a massive solar flare with a huge eruptive structure that popped out of it, and you can still see it glowing, as it begins to cool down here. But it was just a massive structure. You can see again here is when the white light ribbons just started. You can almost see the post-eruptive arcades from this structure that lifted off in here. The whole thing lifted off, and then you can see it quieting down, but you can still see some stuff. So it was a very intense event, and to be able to see it from the ground just tells you how energetic it was. So we had that particular event. We actually had 2 different events that occurred back to back, and I think that's partly why this thing lasted as long as it did. There were 3 flares that were measured by, and this is the OGO 3 satellite. We had an M3 at 1817, an X6 at 1846, which had an incredibly long duration, and then an X2 while the second flare was still decaying, because you saw how much stuff was going on. This is going to be a decaying flare over hours. In fact, just recently we had a big flare at the limb of the sun. Just a few days ago we had a big flare at the limb of the sun. If anyone was paying attention, it was like an M6.8, I believe it was. And the post-eruptive arcades just glowed and stretched out. If you were watching the imagery, just stretched out and glowed for hours upon hours upon hours. In fact, 24 hours later, you could still see a faint, the post-eruptive arcades just really glowing. And they were still there. It was faint, but you could still see the evidence that a big solar storm had been launched. And that's very classic of a very strong eruption. So this kind of thing doesn't surprise me. But it just had so much flux, there was just so much going on, so much instability that even having an X6 class launch, having an X6 class flare launching a coronal mass ejection didn't slow it down. It still gave an X2 just a few hours later. That's pretty intense. Usually when they give an X6, an X class flare, it'll be at least a day before it fires something again, even if it's unstable, because oftentimes these regions reconfigure and it calms them down for a little bit, and then the stress builds up and then they fire again. But oftentimes it takes about 24 hours. So this thing was really intense if it was firing within another hour, barely an hour. Now, during the second emission, second and third emission, we had insane radio bursts. Okay, and for those of you who don't know about radio bursts, that's in the solar flare classes, which is, what series is that? Maybe it's the F series, or hell, the F series, I think I do call it the F series. So it's where the flares, where you learn about solar flares. And so you learn about radio bursts as well, because solar flares not only cause problems for our ionosphere with extreme ultraviolet and X-ray light, but you also have these big radio bursts that can come out, especially when the events are extremely energetic. So we had bursts at 606 megahertz, 2 and 7 gigahertz, and 9.8 gigahertz. This in here is in the L band. This would have likely, they have a peak at 2, but this would have likely impacted GPS, GNSS, ADS-B. This might even have impacted ADS-B. So these are frequencies. These are things that we use every day. For those who don't know what ADS-B is, it's a type of transponder that aircraft use, commercial aircraft use. So when you go on Flight Tracker, 24, whatever that's called, and Flight Aware and all that stuff, those are typically ADS-B transponders that you're hearing, and they're chirping at about 1,000 megahertz, right, 1 gigahertz. GPS is 1.5 to 1.2 to 1.5. So if you're peaking at 2, yeah, you're getting that. Satellite phones would have been out. Okay, you start getting up into 7 and 10 gigahertz. Well, now you're going to start worrying about leaking into possibly Starlink, because Starlink is sitting around 12 gigahertz. Lots of spacecraft, their signals come at these frequencies. So, you're impacting a lot of stuff at this time. But back in 1967, we didn't have all this, right? So it didn't impact us the way it would today, okay? But it impacted military, right? Impacted lots of radars. It impacted the SAC. It impacted the scrambling that they were doing, because back in 1967, remember, we were in the Cold War, right? Deep in the Cold War, and they were doing frequent bomber preparation drills. And they had multiple ones. They had exercises ranging from Alpha, Bravo, Coco, and Delta. And you can see it says Alpha exercises including the crew scrambling to their plane, while Bravo included the startup of the aircraft. Coco exercises involved the aircraft actually taxiing and readying to take off. And then Delta obviously gets the planes in the air. Well, the problem is when your primary communication system is HF radio, 6 to 30 megahertz, and you have bursts that are as high as, if not higher, trust me, all those lower bands are drowned. So you're trying to do scrambling, you're trying to do exercises, and you can't get anybody up, and you can't talk to them. You think you're being jammed, right? I mean, this is how tense the situation was back then. So it took scientists to literally talk down NORAD and say, no, please stand down. Don't take your hand off the button. This isn't Russia. And what was worse was that some of the radio bursts were seen as high as 22 gigahertz. And they were intense. They were unbelievably intense. And yeah, this is kind of what I was talking about. If it happened today, it would impact GPS, GNSS, ADS, and this is the frequency at which they're happening. So this is, what is this, frequency in megahertz. This is pretty intense, guys, and you're seeing frequencies that are just unbelievable. So if you want to see more of that, like I said, I'm not going to go through the whole thing. I went through that in excruciating detail in our last mini course. That was, I think, the entire 3 hours we went through it. And I thankfully have forgotten all of that stuff because I had to throw in all the new stuff from the new events, right? Homer says every time I try to learn something new, I push something old out. But it is archived in this series. So even I'll probably go back at some point when I want a refresher and take a look at some of the stuff, because the details are just, they're mind-boggling. So the 1976 or 1967 event, the takeaways from this particular event was that it was the largest solar radio burst of the 20th century at, of course, certain frequencies, with fluxes and intensities of those radio bursts going off scale in many cases, and they had to kind of reverse engineer what the peaks of these things were, because their instruments just couldn't go that high. F10, for those amateur radio operators who understand F10.7, the flux rose briefly to about 8,000 solar flux units. I mean, where are we sitting right now? Where are we in our F10.7? About 140? Okay, 140 compared to 8,000? Yeah, tells you the sun really can light up like a light switch when it wants to. And during much more intense solar cycles, it did. Okay, and that's going to be something we're going to bring in. We're going to talk about solar cycle activity over the long term. Okay, military radio technologies were severely impacted, right, because we had multiple bursts, right, and they just kept coming. Oftentimes when we have these big bursts, we'll have one or two and then they're done. But in this case, this particular this active region cluster was very unstable for a long period of time. And so we got, in the mini course, I went over the biggest events, but they're guaranteed there were other solar flares that were happening too from this cluster that were smaller, but also would still chirp at these high frequencies. So it was probably even worse than even the papers pulled out and highlighted. Solar energetic particle deposition caused ionospheric heating and radio communication issues. So we had a very large radiation storm along with it. And it was a decent size between the radiation storm and the geomagnetic storm that happened, which wasn't that strong, but it came on strong. It ended up causing NORAD to lose half their catalog. I think it's down here. I'm sorry, I'm jumping. I'm just remembering my favorite part of it. This was the event, and I think I talked about this in the last course. This was the event that taught me that Starlink was going to fall out of the sky. For those who wonder how the hell I knew, years before it was going to happen, this event. Because I knew, and I had been trained on this back when I worked, working at aerospace. My goodness, I was trained on this by 2004, 2005. So I had known this for a very long time, that drag was a huge issue. And people they don't realize that the sun has been very kind to us the last several decades, and it can be a lot meaner. But it's not in that state. It's not in that period of its existence right now. It's in its overall cycles. Okay, the polar cap experienced ongoing communication outages for over a week because the radiation storm lasted that long, and because there were multiple solar storms coming out with probably additional radiation storms being launched and big shock waves in front of these fast CMEs. So it takes radiation storms to die. It takes them a long time to die out. General disruption of ionospheric radio and ground to satellite communication channels were gone for all of May 20 or most of May 23rd and also the 24th and 25th, because there were these multiple CMEs coming. Right, we already talked about the satellite drag effects. And this is for, and I did talk about LEO, right? It's LEO. Drag affects low Earth orbiting spacecraft. And we're getting how many of them up there now? How many constellations are we having now? We didn't have anything like that back then. Imagine today. The near-Earth inner heliosphere was a cosmic ray shadow, meaning a Forbush decrease for more than 2 weeks, which is insane, meaning that we had back-to-back-to-back-to-back coronal mass ejections that kept us in a magnetic bottle and kept the cosmic ray in because cosmic rays don't penetrate big solar storms very easily. And so when we get hit by a CME, by a big solar storm, and we sit inside it, right, we're inside a big shield in a sense, okay, because the shield is very strong magnetic field typically, and it's oftentimes connected to the sun, and so it shields out cosmic rays because they can't penetrate right? Because they got to pay attention to magnetic fields. And so they're shielded out to a great degree. I mean, not completely, but a lot. And so we see at Earth, we see the cosmic ray flux really drop down. And then usually within a few days, it recovers because that CME, or that big solar storm, moves past us, right? It gets over us in about a day or so, and then, slowly the cosmic ray in flux picks back up because that big bubble is no longer blocking a lot of those cosmic rays anymore. But in this case, we must have had back-to-back-to-back CMEs so that we'd go out of one bubble and into another, and then out of that bubble and then into another. So if you're in a Forbush decrease for more than 2 weeks, then that means you not only have one set of active regions, but you have multiple sets of active regions that are separated in longitude, because it takes an active region or an active region cluster 2 weeks to travel all the way across the surface of the sun in Earth view, from east to west limb. That's 2 weeks. So the idea that it was just one set of active regions that was firing all the way across, and it kept you in a cosmic ray shadow, in a Forbush decrease for that long, either this thing was firing Carrington-class events constantly, or at least at the limbs, because that's the only way that you can really be, you have to have a massive solar storm in order to hit Earth if it's firing a solar storm at the edge of the sun, right at the limb of the sun. That CME's got to be massive. When it happens, but it's got to be massive. So it was either doing that when it was at both the east or west limbs, or there were multiple sets of active region clusters that were separated to some degree in longitude, so that while one is transiting across the disk, the other one is just appearing and transiting across the disk. So you have multiple clusters. Don't know about that. That would be a neat thing to chase down. But the idea that being in a Forbush decrease for more than 2 weeks is just, I don't think I've seen that even in my graduate career. There's not a single time I can think of. And I've studied coronal mass ejections pretty seriously since, let's see, I looked at Carrington events, or not Carrington events, but big events, extreme events, since probably the 80s, when I was doing all my graduate work. That was probably the cycle that I studied the most. What is that cycle, like 22, right? 21, 22. So this is a pretty intense thing, just thinking about it. Okay, here at Earth, interradiation belt variations in electron content were still being measured months after the initial event. That's typical, especially interzone stuff probably lasted more than maybe close to a year after these events, because the trapped radiation really gets trapped for a long time. However, the storms were not significant enough to cause GICs. No geomagnetically induced currents, so no notable power grid or utility impacts were recorded. Can you believe that? That's why society kind of went on and never knew anything. The military is sitting there biting their nails, freaking the heck out. But the average citizen there's no substantial aurora, no, grid malfunction, no fires, no nothing, right? So the average person didn't even know. Okay. So that is an example of a very intense Carrington-class event, or set of Carrington events, right? And you'll notice that's what happens, is that oftentimes it's not one event, it's multiple events that have to be oriented the right way, that hit you back to back to back. In this case, it was a bunch of Carrington-class events that were oriented the wrong way. And even though they hit back to back to back, it was really the radio bursts from the flares and the radiation storms driven by the shock waves of these big solar storms coming at us, not the solar storms themselves, that made these events Carrington-class. Okay. Now we're going to flip the script, because as we jump into these next two events, these didn't affect the military so much, but boy did they make pop culture. They made society stand up and go, what? And that's going to be the railway storm in 1921 and the 1941 playoff storm. Okay. Show of hands, how many people have heard of either of these two storms? Anyone? Let's see. I'll pause for a second before we jump into the railway storm. As a matter of fact, I'll go ahead and pop this up with the chat for a moment so we can have some fun and chat for just a second, because that was the review. And I can talk a little bit about the 1972 event, the Apollo Storm 2, if you'd like, during this little Q&A. But I wanted to more kind of, move into the next stuff, so I won't do it too long. Okay. New to me. Nope. Okay, no. So people are saying no. You've not heard of the railway storm or the 1941 playoff storm. This will be fun then. Mickey, you say only the Carrington event. Yep. Only the Carrington event. I see that right here. Dickie says only the Carrington event. Yep. So some people have, right? Oh, yes, great class. Good, thanks, William. Appreciate that. Very new to me. Bayo Hunter, interesting. Okay. So some people have heard them. Yeah, and some people haven't. Just in passing, no details. Okay. And nope, thank you, Aris. I appreciate that. Someone has a hand up. Okay, Nick, you say hand up. Yep, you guys have heard of them, huh? So some people have and some people haven't. Yes, there has been, there was a telegraphy, is that a word? Telegraphic? Yeah. There was definitely disruption there. Lots of communication disruptions. And we'll talk about that in terms of satellites and next gen type stuff, because when you think about it, and like I said, I'll talk about this a little bit later. But when you think about it, today's modern telegraph system is not the power lines. A lot of people say, well, we don't have the telegraph system, but we do have the power lines. And somebody say, well, okay, maybe it's the rail system. Ooh, hint, hint. No, still not that. When you think about it today, right, our anything that's telegraph and communication, that unbroken communication over, the entire globe, right, that's becoming our satellites. That's becoming our low Earth orbiting satellites communicating, okay, talking to each other and then talking to the ground. So it's once again, we're building in a kind of susceptibility to these big events by having unbroken communication that really relies on lots of connectivity being functional. And if you lose a huge section of that, or you lose a hub of that in one time, then what? Right? So it's something we'll talk about as we continue to move on and we talk more about modern times. So who would have heard? Spock's daughter said, who would have heard? I missed. Who would have heard about the railway storms and the playoff storm? Not too many people. If you're, the geomagnetic blitz. That's very right, Pete. I will even be using that because thanks to Jeff Love, he has a paper called the geomagnetic blitz, and that's one of the ones I will be highlighting. But unless you're a history buff or a newspaper buff, you're probably not going to know about it. Not because everybody who knew about it or lived through it could likely be dead by now, right? We didn't have a lot. It was so funny during the research for these storms, reading some of the scientific takes back then, where they were saying, well, we don't really know how the storms are occurring. We don't have a good scientific interpretation of why, but we do know it's solar related. It's most likely due to the emanation of things coming off of the sun and the electrified blah, 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 doing something to our atmosphere and blah, blah, blah. It's just kind of silly how they'd sit there and speculate. And yeah, they've kind of got it right, but they just had no functional representation of how something on the sun got to Earth, right? That was just nebulous space for them. So it's very, very interesting. And so I think that's a good segue in this case, because especially as we start with the railway storm, right, back in 1921, there isn't a lot available when it comes to scientific rigorous analysis, okay, because there's just not a lot of data. Back then we had magnetometers, that's about it. And some of those, and then we had a few telescopes here and there. But if you have a cloudy day, you're done, right? And if the magnetometer didn't work, or if it wasn't set to register a really strong current, it would go off scale. So what you had? You had basically logs, okay? So as I mentioned clear back in A1, in the very first set of class, the very first class I did of this series, I said some of these historic events are going to be very black and white. And what I meant by that, excuse me, what I meant by that was that, excuse me, goodness. What I meant by that was that it was going to be a lot of paper. There's going to not be a lot of really beautiful colored figures and stuff like that, because it was going to be more text on paper, because that's what we had back then. Okay, and yes, we will see that. So I've done the best I could with the scientific analysis, but again, most of this for the next two events are going to be a little bit lighter in flavor. It's going to be more about pop culture and the impacts that they had on society. Okay. All right. Maybe Tom says maybe the tale of the boomers, but science was truthful and readily shared when I was a kid. Yeah, I know how times have changed, sadly, in some cases. The internet is both a blessing and a curse. There's a lot of plagiarism that goes on too now. I didn't think that would happen nearly to the degree that it has. But there's a lot of plagiarism, and then people steal stuff, try to make it their own, and put twists on it that then literally change the truth. Just anyway, it's getting harder to sort the truth from the fiction. The wheat from the chaff, so to speak. All right. Let me go ahead. Let me go ahead and put this back here. And let's just jump into it. Okay. So let me set the stage. Okay. This is back in 1921. And rail systems were absolutely integral to society. And I've got pictures up here to kind of give you a sense of really what the technology was, right? We had steam engines, we had massive locomotives that were, we had as well cargo as well as passenger trains. They were coal-driven, steam-driven. I think steam was going out, but most of these, like you could see here, these are all coal-driven now by the heavy black soot. Passenger cars were, they were pretty modest, right? Not a lot of amenities, but here's some interesting views. No computers, obviously, right? No telephones. This was how people got from place to place, right? Cars were hardly invented at this time. I mean, they were, but they weren't they weren't everywhere. The road system wasn't nearly as well developed as the train system. And this is mainly in the United States. And part of the reason why I'm going over this and trying to and you'll see as I continue talking about this, is that at least in the United States, we've kind of lost, in many areas, we've kind of lost the sense of how much trains dominated the landscape, the transportation landscape of the earliest, the early 20th century. Europe may not have forgotten, because trains are much more integral to European society than they are to the American society. But at one point, trains were really the way to go. And here is just a nice representation of, what a typical station, how many people were here. I mean, these were, this was the way people lived their lives, was focused very much around trains. So much so that the very next year after the 1921 event, there was a great railroad strike of 1922, okay? And it was a massive strike. The strike had and here's some of the working class, right? Talking about railroad workers. It was in response to wage cuts. The unions went on strike, and 400,000 workers walked off the job. Okay, this is in July of that year, of 1922. The railroad companies, it says, with the support of the federal government, brought in strike breakers to fill the slots, right? Because if you have almost 500,000 people walking off the job, you're getting to understand that this is not a small, railroads were not a small thing, not a small business. They were a massive business in the 1920s, okay? Obviously, violence would break out, right? But in the end, people died during this strike because they would fight the railroad strikers. Even their families would come up. I mean, the whole family would be there fighting and picketing and all of that. And by the end of the strike, it said at least 10 people had been killed. and mostly those have been strikers and their families. So the railroad was a huge operation, right? It was central to people's livelihoods. And so it was a mainstay of people's existence, right? And these are the kinds of people that worked on it, right? Oops, and you know what, I have a clicker I can use. So you can see these guys working on it. Look at the machinery, right? Clunky, huge, massive, right? Very, very intense. Anybody who has old artifacts or old technology from, that era, from 100 years ago, knows how heavy they were, right? How everything was super heavy, very dense metals, very thick machinery, and that was just the technology of the day. It's nothing like what we have now, with our little semiconductors and all these little teeny lightweight parts and things built of aluminum and plastic. None of that back in the day. Right? I'm not even sure we had plastics back in the 1920s. I don't think so. I think they came out in the 40s or 50s, right? With Tupperware, stuff like that. So that kind of stuff just didn't exist, right? And look at this. I mean, talk about, and I don't know if this was actually during the strike itself, but as you can see, this is just crazy. People trying to pop into a rail car. This is probably rush hour traffic. For those of you who are familiar with rush hour traffic being cars on a freeway, this was the equivalent, the 1920s equivalent of rush hour traffic. Okay? So if that doesn't give you a sense of how incredibly central the railway system in the 1920s was to American life, if not even European life, but definitely American life, but definitely, but even that worldwide pretty much, because of the technology of the day. This should help kind of frame that for you. Okay. So let's talk a little bit about the activity timeline. For those who are, again, reasonably new to the stuff that I talk about, to these mini courses, I did do a course on the heliosphere, the breathing heliosphere, and it's really about the solar cycle. So here is an example of our sun, because our sun doesn't stay the same throughout the years. It goes through at about 11-year cycle, where it goes from reasonably quiet, like you see here in 2010, to extremely noisy, with lots of active regions and stuff all over it, as you can see here in 2014 and 2015. This was solar maximum in cycle 24, and then it calms back down to something extremely quiet, like you see here in 2020 with this sun. Okay, very, very little, no even active regions visible. And that's our solar cycle, what is called the Schwabe solar cycle. And there are many of them, many different types of cycles, but this is the most common. It's the one that really dictates solar activity, or is really the clock of solar activity, I should say. I want to be a little bit careful because our sun's activity cycle really is made up of lots of stuff. But it's the classic one that everybody follows, where you have sunspot number, in this case on this vertical axis going up, you have time going this way, and you have solar cycles going, the Schwabe cycle going up to a maximum, and then going back down to a minimum, and then going back up to a maximum every 11-ish years, right? Cycle varies from about 9 years to 14 years. And like I said, there's lots of things that modulate the cycle. And there's lots of other ways to talk about the Schwabe cycle. You can talk about the Hale cycle, which is 22 years. It's two of these. Because the cycle, if you look at it magnetically, the cycle starts with North Pole, let's say. It'll start with magnetic north in the North Pole, magnetic south in the South Pole, and then 11 years it takes to reverse that. And then that's half of a Hale cycle, and then it reverses again to get north back up here. And that takes 22 years. So you see it go up, and then the fields are reversed when you get down into the minimum, and then it goes up again, and it's reversing, and then when you get down here, it's back to being what it was 2 cycles ago, magnetically. So the magnetic signature of the sun, the global polar field of the sun, here is the same as here, okay? Because it takes 2 cycles, because you have to reverse and then reverse again. Okay. As you're reversing, just so you know, as you're reversing, you're getting to solar maximum. Sun's magnetic field, when it gets crazy like that, turns into kind of what looks like a lava lamp. And that's when space weather is really nuts. and then it quiets back down when it's nice and ordered by a dipole field. Similar to what the Earth's magnetic field is doing, it's just the sun does it every 11 years. I don't know why people are freaking out so much about the Earth magnetic field flipping. The sun does it every 11 years, people. And it's completely fine. Okay, anyway. So, where was the May 1921 geomagnetic storm? Where did that big storm occur? Right about here, on the declining phase of the solar cycle, which, by the way, is pretty commonplace for these really extreme events to occur. When we look at it from a perspective of a longer range solar cycle activity, okay? This is starting from, it's like 1750. You can see the Schwab cycle going up, down, up, down, up, down. Okay, so these are now all the different cycles. And I think this is probably cycle 1, 2, 3, 4, to, so what are we, cycle 15 was when we had the superstorm, yeah, 15. So here's the cycle where we had the Carrington class event, and then we have the superstorm, the 1921 railway storm. Not a very big cycle, neither was the one where we had the Carrington class event. And then here's another one in 2001 and 2003. We also had the railway storm, I believe is this going to be this cycle right here. We'll see that very shortly. Notice where some of these big storms are, the cycles aren't that big, okay? Because this is average sunspot number, right? And so these are either average or slightly below average for where some of these big storms are. So you can see where you kind of go up. There's a modulation that really kind of envelopes these cycles, right? Okay, you see that modulation. That is another set of cycles. We call them pseudo-cycles because they kind of slosh about a mean, as Scott McIntosh likes to say. And there's lots of different reasons why they are what they are. And we don't know and understand all of those reasons yet, but we're getting better, okay? But the thing to take away here is that many of the most extreme storms on record occurred during smaller than average cycles or average cycles. And that tells us that low activity cycles are particularly conducive to produce extreme events, okay? Which is one of the reasons why we're kind of on guard, right? Because the cycle that we have right now, well, the cycle we just got out of, we produced at least 2.5, if not 3 Carrington class events. And one of them is a very famous one in 2012. And that event, made the headlines because we actually had a spacecraft. It didn't hit Earth, but we had a spacecraft that it passed over, and we saw how strong the magnetic field and the orientation of the field. So we knew that if it hit Earth, it would have been given us a big wallop. So that one made the news because we could talk about it scientifically. But the other two, one of them actually did graze us, and that was one that occurred on September, well, it was launched on September 10th with the second largest flare of that solar cycle. I've talked about it many times. This was during, and it was horrible because even though it barely grazed us, this particular Carrington class event, it didn't cause that much disruption at Earth, but had it hit us head on, this was exactly during Harvey, Irma, and Marie, if you guys remember those hurricanes back in 2017. Also the declining phase of the solar cycle, right? Just like these were, like this one we're going to talk about, and the 1941, for example. But these events, or this event in 2017, if it had hit us head on, it would have completely destroyed our ability to communicate with all of the people that were facing horrible times in Puerto Rico and in Texas, because they were dealing with a catastrophic terrestrial weather event. And that's my biggest concern, is that we're going to have a Carrington class event during one of those, and we're going to be in a horrible shape trying to do search and rescue and yeah, all of that. I've talked about it so many times, I don't want to belabor that because I've got to get moving. But one of the issues that we're having now is that not only were we in a lower than average activity cycle for last cycle 24, but now that we're moving into cycle 25, yeah, it's a little bit bigger. It's a little bit better than cycle 24, but it's still less than average. It may be average, maybe. Kind of hard to tell quite yet, but we're getting close to solar maximum, and man, it may be still slightly below average, to be totally honest. So yeah, that's one of the issues, is that we are still in a low activity cycle, and so the risk for Carrington class events is still quite high. Okay, so we'll see what happens in this cycle. All right, so solar observations of May 1921. Here's one paper by, oh gosh, I can't pronounce his name. Lundstedt. Sorry about this if I completely butchered your name. I apologize. But you can get an Analyses Geophysicae, and I didn't take a lot out of his paper, or their paper rather, but they had really nice analyses and really nice, you know, they did really well with the imagery, and not only took the time to pull it out and show it quite well, but they also and did some really decent flare analysis and spot analysis. But they also took it. I think this was also their paper. Yeah, Lundstedt et al. They took the data and actually put it in a really easy format to read, and colored the magnetic the differences, the magnetic regions, so that we could see how at least the main structure of the spot as it, or cluster, as it rotated, you know, over time from basically the 12th of May, as you can see here, through the 16th of May, how it changed and grew or decayed over time. And this cluster, one of the things I always talk about when I'm talking about magnetic field, is that you never like it when magnetic field, polarities mix, right? And you never like it when they form really tight lines and they're really close together. And so there was a lot of magnetic mixing. Things changed quite dramatically over time. And you can see it does decay, and the reason why it's decaying is because it's causing lots of or likely causing lots of flares. Sadly, a lot of this had to be reconstructed just from visual images, right? So this is their best analysis, using not only the data that they had, but also models. They had to do a topological model to try to reconstruct and reverse engineer what the magnetic configuration must have been. So I thought that was really kind of brilliant and bold and brave of them, because that's really tough to do when you have images like this, right? Back in the day when we didn't have the space telescopes that could do magnetic imaging, you know, Doppler shifting and I won't get into it, but do imaging of telling whether or not the magnetic field is either coming out toward Earth or going in toward Earth, like we have today with the HMI instrument. They literally had to kind of use models, magnetic field models of just the active region, and say, okay, if you had spots that looked like this with the strengths that they calibrated, what would they be? What kind of magnetic configuration would you have? And so they were able to kind of reverse engineer that. Sadly, I don't think we had a lot of, we didn't have a lot of information about the solar flare. I think there's one, I'm trying to remember if in this one, we'll come to it because I'll have the actual slide come up that will talk about it. I can't remember if we have actual data on an actual flare occurring. There was one paper that said that we found a magnetic crochet, but sadly that's oftentimes what has to happen, is that you'll have these big flares occur, and if they're not white light flares and you only have a ground-based telescope, you won't know when the flare occurred, except through looking at magnetometer data. You'll have something called a magnetic crochet. And what that is it's a small little dip in the magnetometer, and it's because what happens is overhead, essentially very close to where that you know, just straight up in altitude, where that magnetometer is lying, if you have a change in the ionosphere that's dramatic enough, then your electron flux, okay, I'm not trying to get too detailed, but the electron flux increases, because what happens is that you have, remember we talked about that solar flux, when you have the solar flares, really increases, and the X-ray flux and the EUV flux, right? Well, when you have that flux increasing, especially in X-ray and EUV, what happens is that the atmosphere absorbs it, right, because that's its job. So it absorbs all that stuff. It doesn't reach the ground, but in absorbing it, it liberates electrons. So now you have a lot more electron flux floating around up there. Well, that electron flux, not only is it an electric current, right, and that's moving, but it's going to create, because it's a moving current, it's a moving electric field changing in time, you're going to create a magnetic field change. And that magnetic field change can be registered and measured at the ground. If it's a local thing, it'll be registered on the ground. So you can see these dips in the magnetic field and magnetometers from these very short-lived dips because of the ionization of the upper atmosphere, okay, during solar flares. Now, does that create like huge weather patterns? No, no, no. These things don't last long enough, right? And the electrons disperse because, you know, they don't like to be what we call anisotropic, you know, gosh, I can't say things today. They don't like anisotropies. So what ends up happening is that these things there's all sorts of mechanisms by way we isotropize, I want to say thermalize, we redistribute, you know, or the upper atmosphere will redistribute these populations of electrons because they want to lower the energy. So things will move through electric and magnetic fields, and that will redistribute these populations reasonably quickly. Okay, so that magnetic crochet only lasts for a short period of time, but it's enough of a signature that you can say, ah, there's the flare. And just like we did back in, as a matter of fact, I can go to it. Those of you who recall, I think I have it in here, yeah, for the 1859 event, right? There's a crochet. Okay, so in this case, it's a peak. Okay, sometimes you can flip it over and it's a dip, however you want to look at it. Okay, but the magnetic crochet is a signature of the solar flare, and what people do then typically with old data is that they'll look for that magnetic crochet, and then they'll calculate to when the storm actually hits. They'll see when the storm hits, and then they'll calculate basically the time it took, right? And then what, for instance, in that old paper is that they'll say, okay, well, was this storm, was it launched straight at Earth, or was it launched at an angle? And, you know, that then they're able to kind of backtrack how fast the storm was actually moving at its apex. Okay, so that's how that was done. And again, I talk about it a lot more intensely in the first class, A1. Okay. But anyway, in this case, I don't know if they found a magnetic crochet. And sadly, when you have solar flares occurring that may or may not be white light flares, well, you may or may not see the magnetic crochet. So reconstruction becomes painful because that's, you know, you can only do what you can do. And yeah, and I think that's all we had with this one. I don't think there was an indicator of the solar flare, but like I said, I'll pull it up. There's going to see, so now, okay, because that's all we can do right now with the active region is just active region cluster is just know when the probability for solar flares are going to be high. Okay. The next take is to go back to the records, and this is why I'm pulling up Mike Hapgood's paper, because he did such an amazing job. Oh my gosh! For those of you who know Mike or have heard of Mike, he's one of the heads of the MOSWAC, if I recall. Oh, he's at Rouse. Well, in this case, he's at Rouse Space. I wonder if he's still there. But Mike Hapgood is one of the chief, like I would consider him one of the chief scientists at MOSWAC. And if that's completely wrong, I apologize, Mike. But I've seen you associated with MOSWAC so much. You've done so much for that group. That's MOSWAC is the Met Office Space Operations Center or Space Weather Operations Center, and they're basically like the SWPC for the UK. So he's one of the leaders there, and as well as, you know, obviously working at RAL. But RAL, the Rutherford Appleton Laboratory, sorry. But he did an amazing job with this paper because he went through so many logs, and we'll talk about them. I'll show you some of the logs. But it's just fascinating seeing the recounts of this stuff and how unbelievably worldwide, how many effects that were felt and what happened. But to just kind of set the stage again, this particular event and the 1941 event, as you will see, the solar flare effects are not the focus, unlike pretty much all the other events that we talked about, right? We talked about the 1859. I was able to talk about the white light flare. I mean, that was Richard Carrington, right? 1972, we were able to know and have evidence of that flare, right? And even in the 1967 event, we were able to talk about the flare. In fact, the flare took center stage because in the 1967 event, that was the radio burst, right? Those were the radio bursts that were really blocking all the military communications. Here, military communications for the solar flare, we didn't even know, right? There's no record of anything totally outrageous at that time. But there was a big sunspot group, there's no doubt. But what ended up happening is that once the big solar storm hit Earth, okay, that's when all hell went, that's when things went to hell in a handbasket, okay? So in this case, we're not looking so much at the solar flare and all that. We don't care if it's X class, we don't care if it's M class, we don't care about white light. That's not what the key is. The key is when the solar storm, the CME, hits, how bad is it? Okay. And just like in the other cases, this particular storm was actually more than one. And that's what the big thing with geomagnetic storms is. You'll find that it's when you have back-to-back-to-back storms and you have to be storming for a sustained period of time. That's the bad bit when it comes to ground effects at Earth. Okay, so when you're talking about geomagnetically induced currents, right, and you're talking about aurora reaching the equator, and you're talking about being able to read by it, right, that's when you have a geomagnetic storm, a big solar storm hit Earth, and then another one hitting, and then another one hitting. And it's just bam, 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 and it just ramps things up so intensely, okay? But that's a totally different, quantitative measure of what a Carrington class event is compared to the ones that we've already studied. Okay? And so you'll see what this is like. Okay. So, like any good worldwide impact introduction, you start with a map. Yes, all of these places, these are locations of magnetic observatories or locations where there were observations being made and that were logged of having particular impacts. Some of these impacts were pretty intense, okay? And these are referred to in the Hapgood paper, they're referred to in a table. But it's one thing you should look at right away. There's a very wide berth, right? Not only is it worldwide, but it's also at a buttload of different latitudes. Pardon my language. Right? You're dealing with high latitude stuff, obviously, right? You're seeing stuff in Sweden and all that stuff, but you're also seeing stuff clear down to Samoa, okay? And you're seeing stuff in the Southern Hemisphere. I mean, this is in 1921. Right, when you don't have that many people reporting from the Southern Hemisphere, stuff even in New Zealand. Okay, so just think of that. I mean, this would be an incredible reporting of stuff today. That'd be a big storm if we saw stuff like this reported today. But this is 1921, when reports are even more sparse. Imagine how populated this map would be if this had been a current event. Okay, with how connected we are. All right. So, like I said, we're going to go into logs, sadly, and I'm probably going to have to lean forward and read some of this to you because I did not have time necessarily to go in and, gosh, I should have made this bigger. I did not have time to go in and make and highlight a bunch of this stuff. Come on, give me a break. Yeah, that made it so much bigger for me to read. It's easy for me if I'm standing like this, but it's hard for me if I'm way back here. So. For those who, and the Hapgood paper is open. Let me go back to show for those who might want to read along. If you type this up in in Google, you can pull this paper down. Okay, it's open literature. I always try to give you articles that are open so that you guys can read along if you like. So Mike Hapgood, just look at Great Storm of May 1921 and then type in Mike Hapgood, and you should be able to pull that paper up. Okay. So one of the things we'll learn very, very quickly is that this paper had, or that you'll see that this particular storm series had a lot of different impacts. Okay, you'll see quickly that we had many what we call sudden storm commencements. Okay, that'll be labeled, and I'll talk about them more in a minute. But that means that many solar storms hit Earth in a very short time window, over the course of like 2 or 3 days. 2 days, about 2 days. We had multiple EMPs. Okay, those of you remember, when you have, this is what the 1972 event did. You have a very fast storm. Remember, the 1972 event was the fastest on record, right? Got to Earth in less than 15 hours, a little over 14, I think it was. So that hit Earth super, super hard. But what it didn't do was cause a lot of storming at Earth. Okay, it had a very strong radiation storm with it because it was very fast moving, had a very strong shock, so it was able to accelerate all those particles. But it hit Earth like a bumper car because it was oriented the wrong way. So when magnets that have the wrong polarity, right, if the magnets have the same polarity, you push them together, they don't like to push, right? It's when they're reversed that they click. Well, the 1972 event had a polarity that was the same, essentially the same as Earth, and so when it hit Earth, it boing, bounced really hard, smacked it really hard, and then, you know, didn't really pump its energy into the Earth system because it couldn't, because the two magnetic systems remained separate for the most part. And so, for the most part. And so what happens when that occurs is that you get very strong, like an impulse, like a very big compression of the Earth's magnetic system. When you do that, it causes the Earth's magnetic system to shrink, right, push down, especially in the front of the nose of the Earth's magnetic system where the CME is hitting. And that compression causes the magnetic field strength to go way up real fast. Well, you do that real fast, that's essentially going to create an EMP at Earth. In fact, an EMP typically at low latitudes. Okay. The reason for that is that you change the Earth's magnetic field strength really quickly, that's going to induce an electric field. Okay. And there you go. There's your EMP, your electromagnetic pulse. So you create an electric field that didn't exist, and it goes woo like that, and it just takes out stuff. Okay. Now, granted, the electromagnetic pulse associated with a geomagnetic storm, right, or associated with a big CME hitting Earth, is not nearly as fast as, let's say, lightning, or a nuclear detonation. It's called, in our case, it's an E3 component, the slowest of the 3 components. So it's not that fast, but it's fast enough to cause issues for grids and railway systems and anything that has a long line made of metal, anything conducting that could act like an antenna or can have current induced into it. Those things are going to have problems, right, when it's hundreds and hundreds of miles. And as you'll see, railway systems, what do they have? These tracks, right? These tracks that go hundreds and hundreds of miles, and they're unbroken, right? Otherwise a train would fall off. Ooh, that sounds like a recipe for geomagnetically induced currents. Sure enough. So we had many sudden storm commencements. They end up creating EMPs because when the sudden storm commencements, when the CME hits Earth and causes that initial impulse, okay? That creates the multiple EMPs. We also had sustained GICs, the geomagnetically induced currents that we've talked about many times in the past. When I talk about that, and you want to know more about those, that's in the E series for Earth because they're ground-induced problems, so I called it the E series for Earth, not to get them confused with G for geomagnetic storm. But when we talk about GICs, they aren't induced directly into the lines, irrespective of whether it's power lines or railway. They're induced into the ground, and then anything that is anchored into the ground, right, for like a ground, when you have a ground for a lightning rod, or a ground for, in this case, railway, or a ground for power transformers. When it's grounded, then that's a pathway for the currents that are induced in the rock beneath to come up into whatever system you've got that makes an easier path. Right? Electricity doesn't like to have to conduct through the ground. Electricity likes to conduct through metal, right? Oh, like telegraph wires, or power lines, or railways, tracks, because, well, it's a lot more conductive, right? It's like the difference between a traffic jam on a surface street and getting on the Autobahn or getting on a freeway and it's clear, right? Who wouldn't do that? I would do that. And electrons do that too. So, they don't stay in the rock. They'll whenever they get a chance, they'll jump up into something that has least resistance, right? So that's why we get GICs. Okay. But there were GICs reported for over 48 to 72 hours during this series of storms. Okay, and I'm just going to read for those who, I might step out of the field of view here a little bit, or you're just going to see my head, because I can't, like I said, I have to try to read this close up. So as we take a look at the numbers, right, in this case here is Canada. Okay, Aginort, Canada. I can't quite read what the city is, but you'll see that over here as number 1. Goodness, where is number 1? In Canada somewhere. Do you see it? There it is. There it is. There's number 1. Okay, so then you can follow number 2, right? You can find it, and number 3, number 4, right? So you're seeing Canada. There's India. There's number 2 over here. Up here, Samoa. You'll see that as 3 over here. There's Samoa. Okay, you can see Hawaii, right? So you just keep going down the list. So these are the ones that are reporting. And so you'll see that they say just crazy things, just absolutely nuts. Like in this case, we're just talking about the geomagnetic field impacts. And in Canada, they're talking about major disturbance range of 118 in H. That's what they're saying right here. This is 118 nanotesla in the horizontal direction of the magnetic field. Anything above 400 or 500 is unbelievable. I mean, even 400 or 500 is pretty intense. It's storming, but you're getting outrageous numbers of magnetic field, and this is due to the magnetic field, which is mainly straight up and down. So now it's causing to wiggle side to side. So you're a magnetic field line, and you're wiggling now back and forth and back and forth. So you're getting a net direction this way and this way. So that's why the magnetometers are saying horizontal, because it's horizontal to the ground. So the H component, okay, this is again something that we learned in the E series of courses, where I talk about the horizontal field component. You have horizontal, vertical, you have declination, inclination. You have all these different ways of talking about it, of defining the different directions of, let's say, the magnetic field as it's measured on the ground. And again, I don't want to go into it in too much detail, because I'll get lost in the weeds, and I know myself. That's why I have to keep stopping myself. So just know that the most important one is the H component, which is the horizontal component, because that's the one that's going to drive currents into the ground, and then those are the ones that are going to come up and cause problems for us, especially when you have east-west facing tracks or power lines or, systems, let's say systems, metal systems. Okay, so 118 nanotesla. This was at Canada, so, way up high, right? India had 230 nanotesla, and they're talking about when it happened. Oh yeah, I'll use my mouse here so you can see. And you can see the times in which these are occurring. So we're talking about station. These are magnetometer stations. Here's the latitude and longitude. Here's the observed activity at and following the large, I think, sudden commencement on the 13th of May. So that's the, it's the same sudden commencement instead of, I call it SSE, sudden storm commencement. So this is a storm commencement, or they're calling it just an SC right there. Okay, hard for me to see in my little monitors here. I apologize, I should have had this bigger. I thought it was going to look a little bit bigger than it does. Okay, anyway, I won't go through all of this, obviously. But as you can see, we're having reports in Honolulu, clear down in Honolulu, Japan, okay? Here's UK, here's France, okay? They're talking about marked oscillation in D of greater than 0.5 degrees, blah, blah, blah. Off the chart in negative direction at 3:30 UT. This is in France, off the charts. The magnetic field is off the charts. The magnetometer can't read it, it's so strong. In the negative direction, oh my goodness, okay, that means that the storm, the auroral oval, is coming down that far. Large positive excursion in D. D is another one of the components. Okay, this is how when you have a bunch of magnetometers, well, if you have a bunch of magnetometers, they will deviate certain ways. If they're above where the, oh boy, careful, Tam. Oh, I don't want to go into L shells. Okay, for those of you who know L shells, right, they map at a certain latitude on the Earth. Okay, so if I were to go and I talk about where this maps, where the L shells are mapping to, the latitudes, the further down in latitude you get, the closer to Earth that maps. The higher in latitude you go, the further out in the Earth's magnetic shield, in this case, yeah, well, in the Earth's magnetic system you map out to. So this is why high latitudes get disturbance first when there's a big geomagnetic storm, is because the outer part of the Earth's magnetic shield is what is mapping to this, okay? And the outer part of the Earth's magnetic shield is what's being rattled by a solar storm on the outside that's trying to get in. But as that storm begins to peel back and kind of what we call peeling back the fluxes of the outer part of the Earth's magnetic shield, it's kind of like peeling layers of an onion, but it doesn't throw them away. It's more like what I've said before, is you flip your bangs back from being in front to behind you. It's just moving them to the back part of you. In this case, it's moving them from the front of the Earth's magnetic system to the tail, okay? So they come back, but for the moment, the solar storm is peeling this flux back and depositing it in the tail. And as it does that, that exposes, close the magnetic field part of the magnetic shield that's closer and closer and closer to Earth. So if you can get stuff that is where storming is rattling out here, and then it begins to come down and then it rattles even more at lower and lower latitudes, what you're seeing is literally the eroding of flux, of magnetic flux from the Earth's magnetic shield, from the outside to the inner heart of the Earth's magnetic system. So by the time you see places like Samoa, right, in low latitudes near the equator, getting hit, getting their magnetic fields going wiggle, 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 right, that's when you know that this magnetic storm this solar storm has eroded, has literally reached into the heart of the Earth's magnetic system. Now, don't worry, it's not ever going to get to the total inside. That doesn't happen. Even when our magnetic field flips, by the way, if it does, we've had people look at what our Earth's magnetic system would be like if the dipole field component went away, completely went away. It's not going to strip our atmosphere off. Our octopole field will protect us. Don't worry about it. But so there are people doing that kind of analysis now. But it doesn't mean that you can't have those fields wiggling. They'll be wiggling and they'll be showing disturbances. Okay, so that's what they're saying here, is when you have the D component in this case down here at France, when you have it showing positive and negative bays and going positive and negative, you're literally seeing the storm reaching down further and further south. So this was in France, which is over here right somewhere in this mess of stuff where you had lots of people reporting. Remember, look how populated Europe was at the time. That's why you got lots of people reporting here. Less so in other regions. Right. Oh, and by the way, this is just page 1. Here's page 2. So it continues to go on, right? So here we have Canada. Here we have Sweden. I think in Sweden it said at 2200 intense activity, minus 150 nanotesla from a sudden storm commencement, followed by intense activity until 800 the next day, particularly between 3 and 600. Range is greater than 1500 1,500, whoops, I'm in the wrong place. Where's my mouse? Right here, guys. 1,500 nanotesla. Greater than. Sweden was off the charts. Okay? Now, of course, they're high latitudes, so yeah, okay, you expect that to some degree, but my goodness, right? And then it says, and at least 700 nanotesla in Z. So over 1,500 nanotesla in H, that's the H component, which is the horizontal component, and over 700 nanotesla in the Z component, which is up, down, vertical. So not only are you seeing the magnetic field wiggling back and forth, but you're seeing it getting compressed, being hit, okay? It's getting stronger and weaker, okay? This was an intense geomagnetic storm, okay? And I love this. In Denmark, if you guys can read the name, it says Rude Skov. Well, I thought I was the only one who was rude. Aren't I rude enough for you? We really need another? But Rude Skov in Denmark said, what is this? Sharp onset of intense activity from 2210, continuing to 800 the next day. Clear depression of H around 100 UT and 200 UT. H is off the chart between 300 and 600. Another depression in H around 700. So here they're saying it starts and then it goes off the chart and then it hits again and it goes off the chart again and another one hit, so they're literally getting pummeled by these multiple back-to-back-to-back CMEs, and they're all intense, they're all strong, because in this case all of them came from the same region or same cluster, and it was the magnetic field in this cluster that we talked about was such that the CMEs being launched were oriented so that they had southward pointing field through a huge part of them. So as the cluster continues launching CMEs, well, every time it launches a coronal mass ejection, it loads, it's like a gun, with a magazine, like an automatic rifle. It loads the chamber with the next bullet. And that bullet typically looks very similar to the bullet that just fired. So as you launch a CME that has a lot of southward field in it, that CME goes off and the system is kind of recovering, but it's loading the chamber with another bullet that looks just like the CME that you just launched. So this bullet that's ready to fire is going to also have a lot of southward magnetic field. So now you got two after it, and now it loads the chamber again with another bullet. Now it fires again. Okay, so this thing kept firing CMEs. They all had southward field. So this is why you had not only a ton of people saying at these stations that bang, we got hit, and then it went intense. And then bang, we got hit again, and it went intense. And and they just keep saying it happened here and here and here. And it's also how you know, why you got it all over the globe. Because for those of you who are getting more familiar with big geomagnetic storms, the biggest intensity of these storms typically occurs at night, right? Especially aurora, right? Well, if you only get hit by one storm, maybe if you're lucky, you'll get aurora in maybe several hemispheres, in two hemispheres, maybe the western hemisphere and the east, maybe, or at least part of it, right? Because it'll last maybe 6 hours or 8 hours. So some, there's a grouping of people in part of the world that gets to see aurora, right? Or have the effects of this stuff. You don't typically get the whole planet. The only way that can happen is if the storming lasts for more than 24, 48, 72 hours. The only way that typically happens is to have multiple CMEs. You don't typically have one ginormous CME that just keeps coming. It's multiple, back to back to back. And every single one of them has a shock wave in front of it. So the Earth just gets hit. It's just like a new getting clocked by George Foreman over and just bam, 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 right? This is how you cause problems when it comes to big geomagnetic storming, big GICs. This is how the power grids get in trouble. This is why every time you guys see me do a forecast and I say, oh, we got a big one coming, or we got a couple CMEs coming, and they're like, oh, it's going to be a killer. And I'm like, no, do we have to worry about power grids? No, this is, if we had, if I saw 3 or 4 really intense eruptions back to back to back to back, then I'd be going, oh, okay, guys, we need to, let's just pay attention to this one. Let's pay attention to this series. We gotta worry about it. But we can have multiple CMEs back to back to back if they're light, they're just okay. Like the most recent series we had, they were all grazing incidences. And I had people telling me, Tamitha, you're asking, oh my gosh, why are you so calm? Why are you smiling? And then all of the CMEs missed us. That's why I'm smiling, is because it's not that big a deal, right? But when you have a big, a nasty actor, one that can create a Carrington event, you want to, that's when you'll see me a bit on edge going, okay, how often is this thing going to fire? Because if it's this angry, is it loading its gun again? Is it getting ready to fire again? That's when you'll see me get like that. If I see multiple CMEs back to back to back, especially if I see one hit us and it's conducive to a big geomagnetic storm because it's got the right magnetic field orientation. And then that same region fires another one. I'll be like, oh boy, okay, there we go. We're probably going to get another one that has a similar configuration. And that's exactly what happened in this case. Okay, so this is probably the first time it is the first time that we talked about a Carrington class event that really, we didn't care about the radiation storms quite so much. We didn't care about the solar flare really all that much at all. So I don't care if it's an X class, an M class, whatever. What I care about is the fact that this thing is launching storms that when they reach Earth, right, and they take days to reach, or hours, in this case, 20 hours or so to reach Earth, that their magnetic field is oriented in such a way that it can pump all of its energy. And every single one of these damned events can pump all of their energies into the Earth's magnetic system. And now the Earth system has to deal with it. Okay, so I'm now, right, I'm on table, second part of this table. Let's see if there's anything else we want to say. So we've got, where's that? Tortosa, Spain? I don't know the city. My apologies. 17. Where are 17? It's in here somewhere. It's in this cluster here somewhere. So this is Spain. What does Spain say? Spain says H is off the chart. I just randomly picked one, right? And because they all say this, right? You think I'm actually got this rehearsed. I don't. H is off the chart from 300 Zulu to 1100 Zulu the next day. So from 300 Zulu in the morning, this is morning time, to, what did they say, 1100 the very next day. That's over 24 hours where the magnetic field is off the chart. The magnetometer can't read anything. The needle is pegged, right? For more than 24 hours. For like 30, what is that? 31 hours? Good Lord. 32 hours? Okay, 660 nanotesla in the H direction. H goes off the chart from 300 and 900 the next day. Range of 600 nanotesla in H, and then minus 160 nanotesla in Z. So the Z direction, that's that's that vertical direction again. Sharp onset of intense activity at 2200 hours. H off the chart after 300 the next day. Okay, now I'm reading a bunch of stuff. So I'm reading that from Spain, I'm reading that from China. Okay, and I'm reading that from Tucson, Arizona. I mean, come on. Not to be left out, Brazil. Could you imagine Brazil today with GPS and all the problems that they have with the South Atlantic anomaly? Good night, and all the activity that goes on there. They have intense activity from 2218 to 1200 the next day. H is off the chart. At times, in both recording devices. Range was 1,000 nanotesla in H and 112 nanotesla in Z. 1,000 nanotesla in Brazil. I mean, right? This is crazy. This, for all practical purposes, is absolutely a Carrington class event. Okay? But it's a Carrington class event in terms of geomagnetic storm now. Not so much, and likely there was a strong radiation storm as well, and we might be going over that. I can't remember, but I don't think there's enough scientific, reporting of it back in this time. So, but HF operators, because remember, HF was obviously, it was a big deal, but we didn't have the wartime stuff going on with HF yet. So we didn't have a Space Weather Prediction Center stood up, which back then was, oh my gosh, wasn't even the SEC. It was called something even before that. But we didn't have any space weather monitoring because that wasn't stood up until basically World War II. And so we didn't have a lot of knowledge. We didn't have a lot of logging of that stuff, right? Especially in the polar regions when radiation storms would occur. These guys didn't even know that there were things like radiation storms, right? They didn't even know the mechanism by which any of this happened. So the 1921 storm timeline. Now, hopefully you guys can see this. It looks reasonably large. But again, you can look at it through your paper if you want. So Hapgood was nice enough to put together kind of like a nice little timeline because there's just so much stuff going on. Okay. And he took the magnetic field deviation of one of the stations. This is Appia, or two of the stations, Appia and Kanoka, I forget. Whoop. Oh, I can't even read it. Kakioka? My apologies. So I know where one is. Appia is in Samoa. Okay, so let's just stick with that because that's the brown one. I mean, and then the Kakioka is Japan. Am I reading that right? Kakio, oh gosh. If you guys can pronounce that properly, I'd be really grateful. It's too small for my eyes, but it looks like it's Kakioka or something like that. So those are the two stations that he has got here, okay? The Samoan station is in red, and the Japanese station is in blue, but there was a data gap. And I don't know if that data gap, I forget, I think the data gap had to do with the storm and either going off scale or just not being able to read it for some reason because power went out or whatever it was, because there's just too many things. And so I'm trying to read it right here. The DAS section of the Appia record replicates a similar but unexplained feature in the published data, perhaps replacement of the photographic paper to record the variation. So you know, obviously there are, not when he was talking about this right here, trying to maybe replace the paper for some reason. You know, everything was done by hand back then, so you're lucky to get the records that you have. So this plot goes from the 14th of May to essentially, what is it, about 1800 on the 15th. Okay, this is 1800 on the 14th, right? 1800 on the 14th to 1800 on the 15th. So in this case, a single day, and that only spans this small period here. Okay. Notice when you look at the full timeline that he's got going, he's talking about the 13th of May, starting here all the way through, you know, past the 16th. Okay. Every single one of these blue lines, vertical blue lines, is indicating a sudden storm commencement. Got it? So from that perspective, just from that alone, you can say there are 4 CMEs, ICMEs hitting, because they're likely shock waves and a big compression where it's smacking the Earth's magnetic field because it's hitting the Earth's magnetic field and causing these very intense compressions. Okay, and that's a sudden storm commencement, boom, and boom. Okay, and you can see some of them in the data. This one you don't see very well, not at Samoa, probably because it wasn't strong enough, but you can see it in other data that's at higher latitudes, right? But here, remember, this magnetometer, this set of magnetometers are the ones that should be reacting pretty much the weakest, because as I explained, right, because we're talking about Samoa and then Japan. I don't know where he put that. What's the one for Japan? Am I stupid? What is the one for Japan? Oh, it is 9, okay. I was almost pointing at 9, but I was like, that. So this one and then this one. Okay, these are the 2 magnetometer readings that you see here. Those are the locations. And remember, as I talked about, right, you have to have storms start up here, okay? And as the storm gets more intense, that roll oval opens, and you know, you get magnetic deviations and wiggles and, you know, problems getting lower and lower and lower in latitude. So you're going to see it in Japan and you're going to see it in Samoa only when you get really strong magnetic field, right? Really strong storming. Okay, magnetometers at higher latitudes we're probably going off scale way too much. In this case, why the Japanese one doesn't go further down and have a stronger signal than the Samoan one, I don't recall if that's just a function of the way it's published, because remember, these magnetometers may not be calibrated with one another. So these may not be intercalibrated well. I think Mac Hapgood managed to do a bit of intercalibration, but I don't recall, because I didn't read all, down into the details as to exactly why the Japanese one isn't much stronger, have a much stronger signal than the Samoan. Excuse me. But nonetheless, we don't really need to know that level of detail. What we need to know is really kind of just the timeline of what's going on, because that's what's critical for what we're talking about. I might actually go back and try to figure out why, because I would have expected the Japanese one to be a stronger signal than the Samoan one. But like I said, it could be intercalibration. So you don't see the sudden storm commencement in either of them here. Again, probably because the sudden storm commencement was registered at high latitudes, but wasn't all that intense, right? But you do start seeing them with the second one. That's what this is, or at least the dip, the original dip, okay? And then you see it another one here, okay, because this thing was recovering a little bit, and then and part of this was well, no, I won't go into say that, but yeah, it might have been part of this rise, might have been part of that sudden storm commencement, because as you crush something, or as you crush the magnetic field, it increases in strength, and so you might be seeing it recovering here, and then it goes down again, and then back up, and then you see maybe a little bit of something here, right? That may be due to this sudden storm commencement here, but the Samoan one didn't respond. So at least with sudden storm commencements, it looks consistent with the Japanese one being at higher latitudes than the Samoan. But they're not significantly different latitudes, right? If the equator is here somewhere, they're almost aligned. This is just the difference is this is so many degrees north, and this is so many degrees, right? This is so many degrees south. Right, if the equator is here. As a matter of fact, we can look at that if we want. Yeah, Samoa, so you can see the latitude and longitude here. So this is almost minus 14 degrees south, and then the Japan one is, oh no, it's a difference, 36.2 degrees north. Okay, so this is significantly further south. It just didn't look like it from the plot, but okay. Okay, anyway, getting back to this. So Samoa will not see the sudden commencements nearly as strongly, you would think, or see all of them if they're weaker, okay? But it's still a nice timeline, so you can see all of them. So we do have 4 different solar storms hitting Earth, boom, 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 all back to back to back to back. And all within, what, 3 days, right? This one hit, you'd have to look at the timeline exactly, but about noon, yeah, a little after, well, right around noon, the first one hit, and then the second one hit just a few hours later on the 13th of May, and then the second one is really the strong one. That storms clear to the almost 0-100 on the 15th, and then this one was also intense. So these 2 are the storms. Obviously, you can tell by all the junk that's in here. These are the 2 storms that really caused big trouble, okay? This first one was just a precursor. Maybe not so much a precursor. When you think about it, it may have been that this set of regions was just beginning to rotate into the Earth's strike zone. And they were firing, it was firing all this time, but this first one, we just got clipped by. That's my guess. Is that the first one we just got clipped by. And the second one was aimed much more right at us, because that thing, all it takes is just to rotate into the Earth strike zone over the course of, a day or so, and yeah, you can get a big difference between the first and second. And that may be why the second one, for example, is much more intense, because it could have been really compressed and catching up to that first one, and so it becomes a much stronger storm. Or that first one could have preconditioned and cleared out a lot of stuff, and the second one hits us. Who knows how many storms this thing fired, this set of regions fired, before even they rotated into the Earth strike zone to actually start hitting us, right? But nonetheless, the second one was likely enhanced by the first. And then the third one was likely enhanced by the second, right? And then by that time, by the time you move out here, it's not that the cluster had rotated out of the Earth strike zone. It's just, maybe it stopped firing. Maybe it gave us a break. Maybe it had a little bit more time. And then by the time it finally fired again, it just wasn't firing. It could also have been firing so many that it finally cleared out all of the overlying field and stuff like that. So it could have still been firing, but it was shooting blank, so to speak, or just shooting nothing, because there just wasn't enough material left to be able to launch. Okay, I've seen that many times. We've seen it in this solar cycle too, where we have big events on the limb and you see a beautiful coronal mass ejection launch on the limb, and that same region continues to fire and rotates into the Earth strike zone, and now it's firing these flares, and there's no CME, nothing. So we just watch flares and deal with radio blackouts, but no big CME comes at us. So that may have been the case here too. It's hard to say. I mean, there's so many different ways that these things expend, you have how their lifetimes evolve. But getting back to the bulk of this, if we look at what's in black, so this is a nice thing that Mike tried to make it really legible. He's talking about this would be, anything in black is the duration of GIC impacts at Earth, okay? And then anything in red is geomagnetic activity. The strongest, most intense will be in heavy pink or heavy red, and then the lighter will be in pink. Okay, so where you have lingering effects. And then auroral observations. So people witnessing aurora happened where you see green. And so you can see during all of this 48 hours, there are so many different effects in so many different places. So he's talking about Sweden, Denmark, New York, and Australia having major GIC issues. Okay, and we'll talk more about that in a minute. So this is where geomagnetic storming was being seen from all of this stuff. Okay, for the geomagnetic field impacts, that's where he's getting all of this. Okay. The other stuff we'll get to in a minute. Okay. Here we have Northwest Europe, Eastern US, and Western US seeing auroral impacts. Okay. Then, as you notice with the second storm, so now the Earth is primed with this. And then when that second CME hit, the ICME hit, right? So this is the first very intense storm. And then when the second one hit, you're going to have another recovery. But when it hit just after that big GIC, or the big sudden storm commencement, which causes those EMPs, now you're getting strong geomagnetic storming again. And now look at this. You have the Karlstad fire. You have Northwest Europe. You have Japan having major GICs with its railway. You have Brazil having major GIC issues. You're having the Brewster fire in New York. So major GIC issues in Eastern US and Canada. Then you have Western US and Canada, right? Because that storm, as the storm progresses, even the areas that weren't as conductive, because the storm is continuing to last, that sustained intensity is building up those GICs and building them up stronger and stronger and stronger. So even in areas that doesn't have nearly as strong a conducive or conductive rock, you're still getting these really big, intense things. And then Australia, we have a fire here. Northwest Europe, you're getting transatlantic radio issues, right? And now you're having all of this aurora being seen, even in New Zealand and Samoa, okay? And then even when the third storm hit, you're getting geomagnetic storm problems. And I forget what the arrows represent. I'm not going to bother with them at the moment. Just because I just realized what time it is. It's like, boy, I've taken a lot of time. Okay, so what was the societal impacts of this, right? And he went through this and he started looking at and put a table to it just like he did before. But now he's talking, this is where we started looking at the logs and seeing where fires were being generated, right, where they were occurring. So in Norway, it says no specific times, but the Fauscher reference includes a letter from Carl Stormer noting the extreme violence of currents in the Norwegian telegraph systems leading to breaks and sparks. So the telegraph systems were sparking. We had in Ireland, we had large earth currents observed in telegraph systems across England, Scotland, and Ireland. We had, in the United States, problems with telegraph systems at Rock Island, Illinois. We had extremely powerful currents in Sweden, right, experiencing practically all telegraph and telephone circuits south of a line passing through Östersund and Söderhamn. Also, in many cases, security devices were destroyed. Security devices? I'm not even sure what kind of security devices those were. And you're seeing the times when these happened. Okay, I mean, and I'm just reading, right? I mean, you guys can read this. Extensive problems on telegraph lines in New Zealand with earth currents driving voltages up to 60 volts. Do you see this? 60 volts, guys. And often showing wide range of fluctuations, and problems could be mitigated by using wired return connections rather than earth return. So in other words, if you decoupled yourself from the ground, you're good. That should be proof right there. Anyone thinks that magnetic storms actually induce currents in wires, it doesn't. It induces it in the ground. Why? The ground is much bigger. You need massive things, okay, to allow currents to build up, basically potential to be built up. And then that can be induced into thin little wires. But if you have small systems, things like pacemakers, things like batteries of your car, things like that, you're not going to have those problems. It's just not going to happen. That's why the Earth it's so critical when you talk about GICs and power grids and things like that you understand the physics involved, because it's too easy with electric and magnetic fields to assume the wrong thing, okay, and then that will throw you off completely. And it also, causes fear-mongering that shouldn't be there. I can't tell you how many Discovery Channel or History Channel shows I've seen where people are talking about how cars' batteries are going to explode and people are going to drop dead because their pacemaker is going to stop working because of the electric currents being induced into there. It's like, oh God, come on, stop. I've even been in one of those shows. I refused to answer the question, so they got someone else. They got Michio Kaku to answer those questions. And of course he answers it like that. And it's like, are you kidding me? I can't win. Okay. Let's see, what else is fun? There was one where here's one in Australia, where earth currents up to 15 milliamps in South Australia. Here's one up with 50 milliamps measured on telegraph lines in Western Australia, alternating with a period of about 20 seconds. Can you imagine that? Alternating, flipping back and forth, because that's how long it takes the Earth's magnetic field to wiggle one way, then wiggle the other way. 20 seconds. But inducing 50 milliamp currents. Now remember the technology that I talked about with the railways? Remember, there was no plastic, there was no aluminum, there's no light metals, small, tiny conductive circuits, right? They were all big, heavy, thick electromechanical machinery, right? So 50 milliamps is bad, but imagine what 50 milliamps would do to a laptop or, right, circuitry. Not a cell phone circuitry. I don't mean a cell phone because it's not wired and touched to the ground. But we have lots of things that are connected to the ground that are based on stuff like this, right? 50 milliamps is pretty intense. Telegraph systems in Paris are unable to receive messages from the rest of Europe or from the United States during the night of the 14th and 15th of May. That's down in here somewhere. Where is that? Come on, right here. Telegraphic communications said to have been said to have been bad at many parts of Japan on the day of the main perturbation of the magnetic storm. I mean, it just goes on and on and on. Okay, telegraph disruptions in Omaha, Nebraska. There's one, I remember reading it. There was one that had some outrageous amount of voltage, and I'm trying to find it. I mean, look at this stuff. I mean, it just goes on and on and on. Okay. Okay, so then we start getting into damage when it comes to railway. Okay. The Albany, it says substantial damage to telegraph and and telephone systems along the Boston-Albany Railroad, especially between Springfield and Albany. Voltages of 400 volts, there we go, 400 volts measured in on, what is that, on some lines in Boston. Okay. I wish I had had time to do all this, to put this all up for you. I'm trying to look for more. Here we go. Here's a fire. Catastrophic damage. This is in Sweden. Catastrophic damage at the telegraph and telephone station at Karlstad. Initially disruption of equipment and some smoke, but later a fire that destroyed the exchange. Analysis by Stenquist indicates the damage required geoelectric fields between 6 and 20 volts per kilometer in Sweden. 6 and 20 volts per kilometer. We have that kind of stuff going on in the 1989 event. Do you guys remember 1989? Where that we call that the standard candle for some of these superstorms. This is what caused the Hydro-Quebec grid to collapse, and people without power for 9 hours. The Toronto Stock Exchange had to quit, had to stop. Hospitals were in terrible condition because they weren't prepared for us to be out of power for that long. You know, and their generators, they didn't have generators like we do now. And then, okay, so Canada, United States, I'm trying to see, here we go. Oh, here we go. Here's one in period of greatest disturbance on telegraph systems across eastern United States, especially at New York and Chicago. Earth current voltages up to 1,000 volts. Did you guys see this? 1,000 volts. Auroral arc overhead of New York at this time. This is a curtain flapping in the wind, was reported in the New York Times. So people were seeing, the same time people were seeing this going on in the skies above them, they were also getting fires and whatnot, and 1,000 volts being put on the telegraph lines. And also, in this case, a lot of the telegraph systems that went down were in railway stations. So, because, you know, railway stations, I mean, that's centralized. You've got a centralized network, and you've got to have communication. So we had the telegraph systems that were anchored to the railway lines. So the railway lines were actually what was inducing, because they were the ones connected to the ground, and they were the ones that were inducing the currents into the lines, and that would get into the telegraph systems, and then it would cause shacks, wooden buildings to catch fire, because the telegraph systems would spark. That would be how they'd spark. On the 15th of May, the railroad station at Brewster in New York State was destroyed by fire attributed to the strong earth currents in telegraph wires. Disruption of telegraph systems in Phoenix, Arizona, from 2000 local time. The telegraph line to Denver was out of action during the night, with a brief recovery, and then it was out again. And then extreme disruption of telegraph systems in western United States, including loss of all services to and from Montana, Helena, Montana, and en routes to Alaska. But severe impacts over a wider area, including Denver, Salt Lake City, San Francisco, Seattle, and Spokane, peaking just before 0700 on the 15th. Okay, so we're talking about damage that has been going on from the 14th through the end of the 15th. And it wasn't until the 16th until things calmed down. Could you imagine, right, when you think about rail systems back then? They were all incredibly complex. Like, this is a station here. You can see all these different lines. They were, you know, this is for cargo, right? They were unbelievably complex with network, you know, with hubs, right? So you'd have a station like this that would go on all these different directions, and you'd have tons of tracks that all had switching mechanisms. Remember, all the switching mechanisms would fail as well. So the trains couldn't work. I mean, not only are they electrified, but the switching mechanisms aren't working, and the telegraph stations and the telegraph systems and the stations in the little, you know, all of the little reporting stations won't be working, because all of that goes down as well. And when you think about how incredibly complex the 1921 rail systems is, this is a map of transportation back in the 1920s, or in 1921 actually. And look at this, just to give you an idea. This right here, which you can't really see, is a timetable, which I blew up right here. Now, you might be able to read this. Gosh, it looked bigger on my computer when I did it. But this timetable is showing routes to and from, oops, who's texting me? Showing routes to and from all of these different locations. Okay, and I mean this is distances. These are not numbers of train numbers, but it's actually miles. So people could take a map like this and calculate, how far it would be to go from here to, let's say, here, right, to these different locations. I mean, this is an incredibly vastly complex system. And on top of that, as I zoom into just certain parts of it, here's the railway systems. This is what I mean by centralized, right? Look at this hub. What city is this? Spokane. Okay. Here's Portland. Do you see how it looks like a spider, right? You've got things coming out in all directions. So with one of these hubs goes down, look at this one. Which one is this one? This is Great Falls. When you have these hubs going down, right? I mean, you're stuck. You can't do anything anywhere because that's how you get interconnected through these places. It's like the only way to get from certain locations. You have to go through that hub. And this is where a lot of this stuff broke down. And then you worry about east-west, right? See lots of the east-west lines? That's where that horizontal movement makes a big difference. And the H component is always the biggest, right? So you're getting an H component. And yeah, because most of the field is coming in basically vertically, so it's going to wiggle mainly east and west. And of course, it'll wiggle north and south too, but east-west is a huge way of that the field wiggles. And look at this once again. This is now the Southern Railroad, so now you're looking at lines in West Virginia and South Carolina, and you're seeing it, right? You're seeing, what are we seeing? Seeing Columbia. What are some of these big cities? Gosh, it's hard for me to read. Birmingham, right? You're seeing these hubs once again, and a lot of east-west. And here's north, the New York City, or New York, central. Look at the big lines, east-west. And I'm sorry, I didn't have a better map. I couldn't find, because I'm trying to find ones of 1921. See how hard this was? Trying to find exactly the right maps. I could not find one of 1921 that was a better map than this. So if I blow it up, it gets all fuzzy. But you can see lots of east-west, right? And Brewster ended up being slightly south. It's not. It's slightly north, I think, of New York City, which we'll talk about in a minute. As a matter of fact, we'll talk about it now. So this was another paper. This was done by Jeff Love. And again, I love the fact that Jeff Love, as well as Hiyashi, I've seen his work too with a lot of the really old events. He does a lot of reconstructions. I love it. So I'm becoming a fan. But they've done a lot of reconstructions of these older events to try to understand GICs better. At least Jeff Love does the GICs. Hiyashi likes to do reconstructions of the physical parameters and indices and things like that. And I just really appreciate it because it's so hard. We always have to reverse engineer when it comes to these events. So here is a nice plot I pulled from their paper that is it's just wonderful because it, in a nutshell, is just showing where some of these things were. Remember the Brewster fire, right? That was the big station where you got, what was it, like 1,000 volts or something? Just insane amount, of voltage just at a single location. As they did the analysis, they actually were able to see how many volts per kilometer, right? So this is now over a large period or large distance. And this is anywhere between 10 and 20 volts per kilometer. And you're seeing where the fire near Brewster, where it took place. I believe it's this line here. And strangely enough, as you'll see, New York City, the lines down in here actually didn't do quite so badly. There's one that's reasonably close in New City, but there was a fire at New York, I think in Central Station, Grand Central Station. There was a fire here too that we'll talk about in just a minute. But was it caused by the storm? That's the trick. So this was during the 14th and 15th of May, I believe, or the 13th and no, the 14th and 15th of May. And so you can see there are quite a few stations that are dealing with almost 20 volts per kilometer, right? But it's not everywhere, and a lot of this is due, right? Like, so you've got basically nothing in this area. This has to do with ground conductivity. if you don't have really strong ground conductivity, I mean, I think it's when it's less conductive that's a problem. I always forget which way it is. If it's less conductive, it's more of a problem, or if it's more conductive, it's more of a problem. I think if it's less conductive, it's more of a problem, but I'm maybe getting it backwards at the moment. But as you can tell, there's a huge difference in the conductivity between the East Coast and then some of these other places that go inland. And so it's harder for, there's certain ground that you actually would prefer to be on so that you don't have to worry about the geomagnetically induced currents. And yeah, my intuition is telling me that if it's more conductive, that's the problem, because you're being able to liberate more electrons that then can move through the lines. And so in some of these areas that had really, massive railroad lines moving, mainly east-west, you're going to be inducing a lot more current than, because of the horizontal, the magnitude of the horizontal magnetic field movement, which then induces, causes an electric field, inducing a potential in the ground, liberating electrons, causing it to be a current, and it's looking for any way to get out of the rock because it wants to move. The Earth's magnetic field is telling it it's got to move, so it's like, okay, I'm going to find a way because it's got to obey, and so it will find a way if it can be through coupled, something that's coupled to the ground. So, what did I have here? Okay, so again, I'm going back to this chart mainly because I wanted to make sure that everybody knew where Apia Samoa was, okay, because we're going to talk about it here in a second. So in the Hapgood paper, I'm going back to the Hapgood paper, talked about the takeaways from this storm, from this incredibly intense storm series. There were basically 3 major periods of geomagnetic activity. We talked about that in the timeline, but there were like 4 different solar storms hitting. It's just that the first one wasn't nearly as intense. It was just maybe that beginning, that maybe a grazing passage or a very weak storm, and it didn't really cause much of a problem for places until when the second storm hit. But all of these periods of geomagnetic activity produced significant effects and impacts at mid-latitudes, and in the case of the first and second peak period, the big ones, the 2 big ones, some outstanding features that are worth highlighting. The first period included the large spike in the depression of the horizontal geomagnetic field. That's what we were talking about. And they said it happened around Copenhagen. That was that first big dip, okay, that you saw at Samoa, but it peaked in Copenhagen. And it produced significant disruption of telephone services between that city and major cities in Sweden. This spike, let's see, I'm not going to go over that. It says that the spike could induce large geomagnetic fields that are now important, that are now an important research target. So as we continue looking at these extreme events, I mean, this is where kind of like why we call it the holy grail of space weather, is if we can predict whether a solar storm is going to have these massive southward pointing magnetic fields because of the potential they have of creating these big GICs, which can absolutely just paralyze economies for days upon days. And that was even back in the 1920s, right? So what does it do today? We don't really know yet. Okay, the second period caused damage in the form of fires. So right when we were going through the list of things that were happening, first we saw these big magnetic field spikes and lots of telegraph issues. And then as the storm just continued, right, and the second storm hit and it exacerbated the first one and made things even worse, well, now things are breaking out into fires because the concurrents and the voltages are continuing to build. Because if you have a storm that is sustained, you're liberating more electrons, in the rock. You're able to shake them loose and build up those potentials even higher and even higher and even higher. And there's no place for these things to go. So they're trying, as they get up into these lines, they are looking for any way to arc and spark and get out. So now the telegraph systems aren't just having breaks in communication. They're now arcing and sparking, okay, and catching things on fire. And it said this posed a significant risk to life. Thus, the second period was truly dangerous, and the driver for the title of this paper. What is the title of this paper? Intensity and impact of the. No, that's Jeff's. What was it? What did he call it? the great storm of May 1921, an exemplar of a dangerous space weather event. Okay, so that's why he put dangerous. He's talking about loss of life. And that, I think, is a really telling thing, especially in 1921, that you can have space weather actually cause a potential for life loss to this degree. In our much more modern age, it's even more significant. Okay, so anyway, he says, okay, it included a number of physical effects, including the following. One, geoelectric fields around 10 volts per kilometer were found to have occurred in Sweden, leading to disruption and damage to Swedish telecommunication networks, especially the one with a fire in Karlstad. Similarly, intense geomagnetic fields occurred in parts of the northeast United States and regions in Canada. This is where he's talking about the fire near the Brewster station, right? And that obviously could have caused more deaths. And then a huge depression, this is the number 3 thing, a huge depression of the equatorial magnetic field at Apia, meaning Samoa, right? Suggesting an extremely large, now this is the scientific part, suggesting an extremely large ring current. While this ring current is not a driver of the large geoelectric fields above, it is important to understand in understanding the low latitude geomagnetic observations. The ring current, for those who have learned in my M courses, my M series, see, this is why this is such an advanced thing. How many different course series have I referenced while doing this particular course? The ring current is basically the energy storage of the Earth's magnetic system, and it's got lots of particles that are kind of swirling in. How do I say this without getting too complicated? It's got a lot of electrons and protons that are swirling in literally a ring around Earth, and without getting too complicated, it's kind of like the Earth's radiation belts, but much lower energy. And there's far more of these particles than there are in the radiation belts that are so much more, famous, right? Everybody knows about the Earth's radiation belts. Well, this is co-located to a great degree with the radiation belts, but doesn't have the individual particles aren't relativistic. These particles have a lot lower energy, but there's just so many of them. And because of that, they end up basically storing most of the energy of the Earth's system. As a geomagnetic storm occurs, this ring current gets energized and more particles get pumped into it, as well as the particles in that ring current get more energized. And the longer you have a storm going, the more energy the particles get and the more particles there are. Okay, particles keep getting injected from the Earth's magnetic tail into this region. And so as this continues and continues, those of you who understand about what a ring of current, because these are particles that are charged, so they're creating, moving charges create a current. And if you have a ring of it, and it's the Earth's magnetic shield that's keeping it as a ring, right? Many of you have seen me use my famous slinky, right, as part of the heart of the Earth's magnetic system. This is a particle accelerator, right? And this is the Earth's magnetic system. And as you have the Earth in this magnetic system sitting in the middle, essentially, of this slinky, you have a particle accelerator. It's like a big CERN accelerator, okay? And it's also trapping the particles in this ring. But as you have particles swirling around in this ring, okay, and I'm saying this loosely because the particles are actually bouncing and drifting, and they're doing lots of things in here, but they're essentially trapped. And as these particles get more energized, more particles get pumped in from the tail, and you get more and more of them. This current that you're creating then induces a magnetic field, okay? That magnetic field that it induces, so it's creating a magnetic field that is vertical, that's straight into the center of this ring. That magnetic field direction that it induces is actually the opposite direction of Earth's magnetic field. And so magnetometers on the ground, especially at low latitudes, like here, okay, or medium to low latitudes, they will sense that magnetic field that the ring current is inducing. And because that ring current serves to lower the overall, the apparent overall strength of the Earth's magnetic field in that region. So these magnetometers actually are registering when they have a dip Okay, here. As they, flip this way. As they see this dip, okay, that dip is actually a measure of how strong is this current, because it's the stronger the current gets, the more that magnetic field, the stronger the magnetic field is, which then subtracts off of the strength of the Earth's magnetic field. So this dips down, gets smaller. Seems counterintuitive, but that's the way it happens, because it's moving. The current is inducing a magnetic field that is the opposite in strength, and so the overall measurement in the equator is for the field strength to go down. Okay, but this is due to the fact that there's so much going on with these geomagnetic storms, so much energy being pumped into that ring current, that the ring current is generating its own magnetic field that's strong enough to compete to some degree with the Earth's magnetic field. You can actually see how much strength it's competing. Okay, and I just mean by additing. It's not really competing with the Earth's shield, but it's something that we measure as scientists. Yeah, it's something that we measure as scientists because it's important to the dynamics of the Earth's magnetic system. But it also is a real tell. When the ring current begins to get that strong, we know that the big storm has been going on for a long time, because the ring current is slow. It's like the brontosaurus of current systems in the Earth's system. It's very slow to move. It's very slow to change, right? It just moves. It's very, it's like corporate America, right? They don't change very quickly. So it takes a long time to pump it up. And so the fact that we were seeing this in Samoa told us a lot about how strong these storms were. And back then, again, that was one of the only ways we were able to tell the intensity, other than, of course, all of the impacts that people logged right back in the day. I was going to say something else about the ring current. Oh, and also, it tells us a lot about aurora, because when you have a very strong ring current, you're going to get that big red SAR arc. If you guys have ever seen the SAR arc, and you talked about it, there was one that wasn't that long ago that we had during a big storm. Those are typically, that subauroral arc is typically, and I'm not talking the Steve phenomena. I'm talking the big red ribbon that is like thick red ribbon that goes in the sky, typically pretty far south of the normal auroral oval. And that big ribbon, that big thick band, is due to the ring current being super, super pumped up. Okay, it's the kind of aurora that it creates. And it creates it in lower latitudes, because that's where the ring current maps, it's the inner heart of the Earth's magnetic system. So for those of you who are aurora fans, you will like the fact that, and I should have brought a picture of this, but you will like the fact that when you see that big SAR arc, you know that storm has gotten to the inner heart of Earth's magnetic system, and it's been pumping its energy in for quite some time. So it's a neat way of visually seeing how hard the Earth is working to keep us all safe, right? To keep that stuff out. Okay, so a cautionary footnote in history. Where there was a storm, there was a fire. I don't know if he marked it here. I don't think so. But there was a fire in the New York station on the 16th, I believe it was. And we were still having a geomagnetic storm. There was still, but notice there were no fires anymore. There was no, not fires, but there were no GICs being reported anymore. So this was a much milder storm. Okay. But strangely enough, and Mike Hapgood mentions this, at the New York Railroad fire. Oh, I guess it is. It says on the 15th of May, 11:04 on the 15th of May. There was a big fire at New York's Grand Central Station. And it says it was followed by a serious fire. Okay. The funny thing is that this destroyed a control tower about 1 kilometer from the Grand Central Station. Trains in and out of this and trains out of the Grand Central Station were significantly delayed because of it. However, it says the disruption was reported in newspapers on May 16th. So yes, this was May 16th. Okay. So the fire occurred on May 16th, I think, and perhaps unsurprisingly was associated by them with the intense geomagnetic activity in the early hours of the 15th. And and that had been widely reported in the papers. But there is no evidence for strong activity in the region around New York. The report of the geomagnetic activity observed in Maryland was 330 kilometers south of New York, southwest of New York. And it says it was that period that they're talking about, Maryland was saying that there was a period of comparative quiet in this time. So Mike went on to say that just because we had a fire at the New York Grand Central Station doesn't necessarily mean that it was associated with that geomagnetic storm. In fact, I think when they talked about it, I think down in here he's talking about some short circuit with a cold water pipe, yeah. It came in contact, something had to do with the third rail, the electrified rail, came in contact with a cold water pipe because they were doing some maintenance, and that caused the fire, or could have caused the fire. So the sad thing is that because it was timed with, in the middle or as the waning part or during a quiet period of this set of geomagnetic storms, this railroad fire in New York, not the Brewster fire, but in New York's Grand Central, it was associated with this storm. And this is something that to me kind of resonated with me because it has become one of the most well-known storms, or well-known fires associated with this storm because it was in New York City. And it's sad because it was probably the only fire that occurred during that period that wasn't caused by the storm. But that's pop culture for you, right? That's astrosociology for you at work. And we see this kind of thing happen, today, right? Anytime we have a big storm occurring, and then some anomaly occurs it's completely unrelated, people will jump to associate it with the geomagnetic storm or with the space weather event that happened. And sometimes it's pretty funny because we could have people will talk about some fire or something that would be associated with a solar storm hitting, and causing a geomagnetic storm. And there's no geomagnetic storm hitting Earth at all. It was just a flare, a big M-class flare, with no storm coming toward Earth at all. And people will still make the connection because, ooh, there was a solar flare and therefore something's hitting Earth, and now we're all in trouble. So even back then in the 1920s, even though there was very little known about space weather at the time and how they affected, this kind of thing was still happening. So I just find that interesting. Okay, auroral sightings. And I won't take too much time to talk about this. But again, there's more in Mike's, he was very, very thorough. And so now he's talking about all the logs of auroral sightings. And of course you see it in Germany for many, many hours. You're seeing it in the UK, seeing it at the zenith, so they're having coronas overhead. In France, it was seen in France. I mean, it's just so fun to read this, and I can stand out of the way so you guys can look at it or take a screenshot or, pause the video at some point and read it because it's just so nuts. But they saw arcs that were all the way across. They saw deep red aurora. We're seeing them in South Carolina. We're seeing them in Germany and clear down to California and Honolulu. I mean, they're just seeing them everywhere. And let's see if I can find some fun. Oh, here's the one with it had the auroral arc overhead, and you had the curtain. It was flapping in the wind, so they had curtains in New York City. This is the time when they were having the Brewster fire. So imagine all of this happening all at the same time. It just would scare you to death, wouldn't it? Especially in 1921, Omaha. The aurora was bright enough to be read by. People were able to read watches by the aurora. Let's see where else. Lots of reports from the United States. Here's Phoenix, Arizona. Okay, brilliant aurora observed from Rock Island in Illinois. Lowell Observatory in northern Arizona. There are scenes in Prescott. Here's the report in Dallas Times of aurora. This is, again, here's Tucson, Arizona again. There's Prescott. Where's this bright aurora observed from ships on Midway from Puget Sound to Honolulu? I mean, come on. Where did you not see aurora? Here's Lick Observatory in California on Mount Hamilton. Red aurora showing up in the southern sky. Oh, where is it? Oh, I don't have it up. I missed one more page. Shoot, there's one more page of this. So it continues. Like I said, there's like 4 pages or 3 pages of this, aren't there? Yeah, 1, 2. Yeah, there's 3 pages of this, and I missed the third page. But as you can see, just from this, take a look at Mike's paper. It's amazing. Sadly, not a lot of pictures, but a ton of reports, just everywhere. And where is all this coming from? Well, here. Look at all the newspapers. I don't think there's a single event that I've seen that had more newspaper articles on the aurora, on what was going on. Sunspots vanishing, due to disappear in 24 hours. This is after everything else. Memphis fires or wires all over the United States affected by visitation. They called it a visitation. Aurora borealis noticed at Little Rock in the first time for years. Okay. Borealis caused sunspots will diminish today. Right? People are scared poopless, going, what's going to happen? We're going to get it tomorrow. Because they didn't realize it's solar storms, so they're thinking it's sunspots. Everything's sunspots, right? Sunspot credited with rail tie-up in New York's central signal system put out of service by play of northern lights. Aurora borealis plays tricks on telegraph wires. This is one of these was in France. This one's Pennsylvania. Gosh, here's one that says Hertz wires, not wireless. Right? Wires hit by the aurora borealis. Sunspot aurora paralyzes wires. Cables damaged by sunspot aurora. These are New York Times, I believe. No, actually these aren't. I'd have to zoom in on this to see where they came from. But there's just, you can find this stuff everywhere. Electric disturbances affect French wires. There's the French one. Aurora not visible. Its absence be attributed to atmospheric conditions. Oh, you mean clouds? You know, again, New York Times here, solar explosion bombards Earth. And another, aurora borealis, both hemispheres affected, telegraphs and telephones influenced by, you know, this is reported in Sydney. So this was a worldwide event, right? Because again, there were so many events, so many solar storms hitting back to back to back to back that the whole world could rotate underneath it. So everybody got a chance to see it. But again, we had, back in the day, it was all rail. And so, you know, because of the railways were such a central part of, at least in the Americas, but also around the world, railways were such an important part of transportation. And because it was the railway systems that were so vulnerable, right, it's called the railway storm, because that's where a lot of fires occurred. And to be totally honest, the damage done was actually worse than the Carrington event. So that's one of the things I wanted to point out with this particular event, was that the worldwide craziness that occurred and the amount of damage and the amount of lives that were potentially put on hold or hurt by this far exceeded the Carrington class event in 1859. But then again, our technology had grown quite a bit, didn't it? We didn't have nearly as extensive railways in 1859 as we did in 1921. So what does that tell us about technology? And the fact that as we rely on it more and as we network and centralize more, we become more vulnerable as a society to the influences of space weather. Okay. So I will pause here. Boy, this was a lot longer review than I thought. Let me go ahead and put the chat back on. So what did you guys think of this part thus far? Was this interesting? Did I go through it too slowly, too quickly? What did you guys think? Let's see. Scared poopless, you're a hoot. Oh boy. Okay, my kitty Sylvester. What are you guys saying here? Oh, somebody's birthday. I didn't realize it was somebody's birthday. That's awesome. Lesson is these CMEs, this is the origin. Lesson is these CMEs happen much more often than generally known, and we are more vulnerable. Yes, absolutely. Oh, good, Mike. You think it's just right? Good. Yeah, you guys are seeing nice, awesome. Appreciate that very much. Just right. Of course, I missed the. Somebody missed something. The vulnerability can be countered somewhat with knowledge. Yes, absolutely. That's why I do this stuff. You guys are saying perfect, quite interesting. Wow. Okay, thank you so much. I'm so glad. 1937, Death Valley. Was that was that another big solar storm? That's Cornelia. Was that a big superstorm? Might have been. There are so many of them. There are really a lot of them. Heidi, you say loved it. Thank you so much, Heidi. That's so kind. Appreciate that. Julian, hell yeah, it's interesting. Good. And congrats, Julian. I hope you get that space weather position. That's so awesome. You got to tell us more about it. So everybody send Julian good vibes because he may be landing a cool position here soon. Interesting. I didn't know about the 1921 or see the one in 41 too. Wow. Yeah, we haven't even gone through the 41. I can go through. We'll go through a little bit of the 41. I mean, we'll see how long my stamina is, or how long your stamina is, as to how far we go into the 41. Oh, let's see. Please do more of these because people are very unaware. Yes, yes, I agree. And it's silly because there are so many of them. Why southward direction is alarming. I'm misunderstanding. I missed who said that. That's up here. That actually is, let's see. Oh, Spock's daughter. Okay, I see you. The reason why it's southward is important is because Earth's magnetic field points northward at the nose of the Earth's magnetic, basically where the solar wind hits Earth. So if I get my cute little slinky again, right, and Earth's sitting in the middle. Let's say the sun is here, okay? The sun is blowing solar wind this way. Okay, hopefully that makes sense. So well, let me do it this way. So I don't have to cross my hands. So let's say the sun's blowing solar wind into it this way, okay? Earth's magnetic field is such that the magnetic north points down. And so as the magnetic field comes out, okay, I'll do it with a pen. Okay, so here's a black pen. So the front of the pen, hello, if you can see the pen, it goes down, okay, that's the magnetic field direction, going down through Earth, okay, so it's going to come out the bottom, okay, so you still see the pen pointing south now. And as it curves back up, because it's a dipole field, this is the way magnetic field curves. It curves just like the slinky shows. It curves back up like this and then goes back in, okay? And it comes out the bottom and curves, it follows the magnetic, follows the slinky, right? The slinky lines come up like this, and then they curve back in, okay? So at the front of the Earth's magnetic system, that magnetic field has turned northward, okay? Right? It's southward here, and then it comes out and it curves northward. So as it's northward, what it needs, so now I'm going to put this down. What it needs, if this is northward, what it needs, if you know magnets, it needs a field of the opposite direction to click, to stick, right? If I have a field coming in this way, they'll repel each other and it'll bounce off. The CME will bounce off, and be what I call a bumper car. But if the magnetic field is reversed, then they'll click and the two magnetic field systems will become one big magnetic field system, and all of the junk that's in that CME now can be pumped into the Earth system, okay? So this direction is south. So the solar wind, or coronal mass ejection, interplanetary coronal mass ejection, magnetic field needs to be pointed south so that it can click with the Earth's magnetic system and do what we call reconnection, okay? And that's what drives really big storms, is if that ICME has the right magnetic configuration to drive, meaning southward mainly, to drive big geomagnetic storms and pump all of its energy into the Earth's magnetic system. And the Earth's magnetic system goes like this, and it shoots a bunch of that stuff into the Earth's upper atmosphere, and it shoots a bunch of that stuff down tail. So if you look at the M series that I've taught, okay, that covers all of that. We go over that in great detail. I do the chicken dance where I talk about magnetic field flux changing. As a matter of fact, if you look on YouTube in my mini courses, you'll see it, because when you hover over the little thumbnails animate on YouTube for the most of, you'll see me doing this. I'm going like this and then this, and I do like this and then back. It's pretty funny. You actually see me doing the chicken dances. Like YouTube had a sense of humor and made the thumbnail the famous chicken dance. So anyway, it's a joke that you'll get when you watch that one. So hopefully that answered that question. Okay, 7 million homes. What is it, Antonio? You say there were in 1921 nearly 7 million homes in the United States wired for electric service, served by 5,600 or 5,000. What is it? Electric light and power companies. The output of 42. Good Lord, what is that, 42 billion kilowatt hours? Wow. Boy, were we. You know, you think 100 years ago that we really weren't all that advanced, but man, that's advanced. But think about how much further we are today, right? And how we, you know, are granted our electronics and everything require less power per device compared to back then, right? Because we don't have these big clunky electromechanical devices that are, you know, solid and thick and heavy and big and all that. But we have so many more of them. I mean, I won't even tell you how many computers I have just in this room alone, right? I can count them on two hands, but just barely. I have quite a few. Actually, if I count my mobile devices, I can't count them on two hands. I got too many of them in here. And that's just in this room. So, you know, it's mind-boggling how much more interconnected and how much more susceptible we are because of the vulnerabilities we have with the types of services that we rely on. I mean, literally rely on. So it's quite interesting to think about that. And that's some stuff that we're going to be getting into as we get finished with this storm. We'll start talking about that. Okay, and I'm hoping I can go through this storm more quickly because this one is a little bit more fun. Okay, this new active region in the southeast limb area of the solar disk should be interesting to watch this week. Yeah, it was, you know, it was really strong on the far side. So I've been watching it too, and I was actually kind of disappointed. I thought some of the active regions that had been rotating into EarthView over the past few days were going to give us more than they gave us. So, you know, I guess the nice thing is that it allowed me to do more work on this mini course, but I was kind of disappointed, to be totally honest. I was hoping we'd get more. September 3rd, 1882. Yes, that was another big one. I think it was 1882 that we had a big solar storm. So there's so many, guys. There's so many. I could go on forever doing this, but I'd rather give you some of the big ones and then move on to some of the ones in the modern era, because I want you to see both the similarities and the differences. Okay, so all right, let me go ahead. Well, if there's no more like monster questions, let me jump into the into the playoff storm. And again, this one I think has even less rigorous scientific stuff about it, but it's kind of fun. It's fun, and it's as you can tell by the time stamp, right? 1941. Where were we? Right, about to enter World War II. So just like the other one, let me set the stage. Okay, September 1941 marks the 2-year anniversary of the invasion of Poland that most people consider the start of World War II. Right, not too many people cared about that, right? Because it wasn't one of the hinging pivotal points of World War II. But it's good to recognize it because it sets the tone for how people were feeling. So already you should kind of harken back to the 1967 storm, right, when that was the Cold War. This might have even been even scarier because there was a World War happening, and Americans were trying to decide whether they were actually going to end up getting into it. In fact, in 1941 in September, we were building the USS Juno. Okay, this is what it looked like. So we were rapidly preparing for war, and we were building military assets as quickly as possible. The press, here's Winnipeg Free Press. Roosevelt pledges full aid. Everything in U.S. power is promised. Lots of stuff. Great general attack launched by Red Army, as you can see here, right? Lots of fear, lots of concern. Okay, and it says, note that the paper already has news of the Soviet offense that began on September 1st in the central sector of the Eastern Front. So people are nervous, right? And I think it's that downward slide of, oh God, we're getting sucked in. It's coming. So at that time, the great political imponderables remained the United States and Japan, right? We were the only two really who hadn't been sucked into it yet. The U.S. is obviously doing everything short of declaring war that it can to help its British allies. We had convoys, Canada and the United States had convoys going to the Brits. A fact that Adolf Hitler did not like, but he couldn't do anything about it. Japan was playing a double game, feigning blind adherence to the German cause and paying lip service to German objectives, while secretly trying to resolve its issues with the Americans, short of getting into the conflict. The Imperial Japanese war effort in China was struggling, but was aided somewhat by internal Chinese conflicts between the nationalists and communist forces. But there was obviously little prospect of Japan subduing China. There would be no hope of that today, suggesting an endless campaign that never threatens Japan but requires constant supplies and reinforcements. So Japan's patience was weakening because they, that was kind of like it's kind of like a Vietnam for them. It would just be lasting forever and never going anywhere. So the tensions were high even on that front. So that hopefully sets the stage to a great degree of where we were as a nation and where the world was in terms of, threats and a threat assessment and jumping to conclusions when something would go off the rails. Okay, where were we in terms of the solar activity timeline? Well, I'm throwing up the same plot as before, but in this case now we're looking at cycle 17, again, declining phase of the solar cycle. What did we talk about with these extreme storms? Solar cycles seem to have last gasps, that as we go down into the declining phase of the cycle, that's when we get these really intense, very extreme events. We had it last cycle too. Remember 2017? That was the declining phase of the solar cycle. Will we likely have something again? Yeah, probably. Will it be a Carrington class event like it was in 2017, but in that case it didn't hit us? Don't know. Okay. We never know with this stuff, right? But just trying to give you hints of the way the sun works. And again, where were we in that case? Because here's 2017, by the way. So this is when the sun launched 2 of the 3 Carrington class events. Here's where the sun launched the first Carrington event of cycle 2014 or cycle 24. Launched 1 in 2012, and it launched 2 in 2017. So the sun solar maximum doesn't typically give us, it gives us extreme events, but it doesn't give us the Carrington class. It doesn't give us the extreme of extreme. It'll give us superstorms. But man, most of the really big ones come out in the declining phase. Okay, so let's take a look at some of the sunspot stuff. Now, again, it's 1940, so we don't have a lot of observations. Okay, I think this is the one where we actually did get something about solar flare, but I had to do a lot of digging in catalogs, which I had to do with the other one too, but this one, at least Mike Hapgood had done most of the digging and really, really comprehensive analysis in that 21 one. But here we go. Take a look. Yuck, right? This is from Mount Wilson. And this is a sunspot cluster. There are actually 2 sets of clusters. That's why they've got this line drawn. As a matter of fact, I'll zoom in. So you've got this line drawn between region 7281 and region 7283. And it was a cluster, right? But look at this mess. Just a total mess. And once again, I mean, look at all these little spots. There's just so many of them. Dot, 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 dot. And I think there's I'll show you a ground-based amateur astronomer who actually talked about there being something like 40 or 50 of these spots. He saw them with his own eyes in this particular cluster that was rotating to the sun's west limb. So you can see this thing being center disk, right, in September 16th, which is the day before the flare occurred. This thing is definitely in the Earth strike zone, okay, and it's big. These cycles, by the way, in the 40s and 50s and 60s, 40, 50, 60, were some of the largest cycles, some of the biggest sunspots were when the biggest sunspots on record are in record. Okay, this is one of the biggest ones, I think. Okay, in fact, when we take a look at the data here, so this is the catalog of sunspots, of the big sunspots with greater than 500. Is it 500? Yeah, 500 millionths of the sun's hemisphere. So that's how they MSH is the official name, millionths of solar hemisphere. So it's done as a ratio. Okay, so this for the big sunspots. They were in here in this catalog, 4 different years. Okay, so you can see. In this case, we're looking at this one. I've highlighted it here. And the interesting thing, not so much where the longitude and latitude is, right? But when you look at here, what's it? The max area of whole spots. Uh-oh. Let me see who's texting me. I gotta make sure nothing's wrong with the feed. Oh no, okay, we're all right. Looks like we're having another solar flare right now. Thanks, Mark. What is it, 3088? Yeah, so max area, that's right there, okay? That max area, if you look at all of this, all of these regions in here, this is when this region, because you can see July, they appeared in July, August, September, October, and November. In September, there was a recurring region, which is 7281, and you can see it here. So 7281. So he's talking about this region, this cluster of stuff. Okay. This is as large as it got, or at least when it was Earthside. It was as large as it got. Okay. 3,000 compared to 1,100 or 1,400 or whatever. And it was definitely part of a recurrent series, because you can see it says recurrent series, and it gave a name of the recurrent series. I don't see that reported on any of this, but I do see that I did verify that, yes, they are talking about this sunspot region here, or the sunspot cluster region. So this was a pretty massive region, by far the largest of the large that you see. In fact, if you look at any of these numbers, all of them on this page, none of them touch this. This is almost 3 times as big. Okay. So this is a big, big, big region. And this time I think I blew it up. So we're looking here at catalog of sunspots. Okay, again, and they had a footnote, and I believe I've made it, didn't I? Yes. See, that's what I should have done with the other ones. Said 1941, September 16th. A great complex group, a beta gamma group, undergoing changes. So that means if it's undergoing changes, that means that we have what we call flux emergence. There's going to be basically, those of you who remember me talking about sunspots, and this comes from sunspots and telescopes. I talked about the suns, how the solar dynamo works, and then we talk about sunspots as essentially as submarines rising up to the surface of the sun, like in this boiling pot of light, light emanating water. And just like a submarine, it'll come up to the surface, and then it will stay up there for a little while, and then it will submerge. And that has to do with how buoyant the magnetic field is and what it's doing when it gets these loops and stuff underneath the surface. But it's the natural progression of sunspots. So they emerge up to the surface, and then they will submerge after they've released enough magnetic energy. They no longer are magnetically buoyant, and so they sink back down, roughly. If any solar physicists are in the room, please forgive me for my layman speak, but that's essentially what we're kind of talking about. And the thing is that oftentimes you can get you can get these submarines that are rising right underneath and coming up into the middle of a grouping that already exists. So it's very similar to having, like, let's say, submarines of a particular country, right, or allied forces, and then imagine the enemy subs emerging right in the middle of this convoy, or right in the middle of this grouping, right? You're immediately going to be firing on it, right? Because if you're stupid enough to do that. But that's kind of the same kind of idea with magnetic field, is that you have, let's say, a cluster of magnetic regions that are of one magnetic polarity, and then what emerges right underneath it is the opposite polarity. Holy merd, now all hell breaks loose, and now you've got flares and everything going off. And as the submarine continues to rise, you're just going to continue to get flaring and flaring and flaring, and you're going to continue to get coronal mass ejections being launched, and all sorts of basically reconfiguration of the Earth's magnetic, or the sun's magnetic system in that cluster, until it's either that threat is neutralized, so to speak, the magnetic flux is eroded and gotten rid of, or it just keeps firing until this damn thing rotates to the sun's far side and you don't have to look at it anymore. Right? So for Earth's practical purposes, just let it go off on the sun's far side. We don't care. But, that takes days, right? From here, we've got probably 7 days before this thing rotates to the sun's far side because this is center disk. So anyway, so that's what they're talking about when they say that this beta gamma group, which is already a little bit unstable when you have gamma, this configuration, it's a little bit unstable, but it's undergoing changes. It says an intense flare of magnitude 3 plus. This is an astronomical way of measuring flare intensity. One of the 35 collectively observed during the group's disk passage. Did you hear that? It's already flared 35 times, or it's going to flare 35 times by the time it, while it's in Earth view. Okay, but one of the flares was observed on September 17th at this time, and a great geomagnetic storm hit Earth or began 20 and a half hours later. Okay, so at least this time they were actually able to observe the flare that occurred. I don't think they had to find a magnetic crochet. They were actually able to observe it, and then they were able to say, okay, this CME or ICME began 20 and a half hours later. And I think when you go back to the Russell et al. Paper, because this was reasonably close to center disk, they didn't have to make much of a correction. So I think it does hit the speed of this particular Carrington event was around 19 to 20 hours, okay, because it was slightly off center, but not by much. Okay, so this is a very fast storm, right? It's going to arrive in less than a day. And yet, sadly, there's not a lot of, that might have been the end of the scientific analysis. Just like the 1921 event, we're talking about a storm that is stronger, or we're talking about a CME and ICME that hits, that has the right magnetic configuration to cause a big geomagnetic storm. In this case, I think that's the right thing, right? Yeah. In this case, what it really impacted, because this was not the heyday, but we were becoming much more aware, and we were using HF radio so much more. We were becoming much more aware of atmospheric disturbances because they happen so much with HF radio. And we were becoming more aware of the scientific basis for which these things occurred. And so we kind of knew, I mean, here's even a fun cartoon. We kind of knew a little bit more about what was going on. So here's a prominence, they're saying prominence of rosy flames, how funny, right? Prominences are just simply filament eruptions that go off to the sun's side, but that's what they were, because that's all they could observe back then. They didn't know, all that much about these big coronal loops and big filament structures that, that were seen on the center disk. They saw them a little bit, but it was a lot easier to see them as an amateur astronomer, seeing them on the limbs, because you could see them in white light as well as some of the more scientific filters. Okay. So this is an enlarged view of a sunspot in a vortex, a whirling magnet. So they knew it was all magnetic fields, right? And yes, sunspots rotate a little bit, and they have fields that come out of them. So it looks like that's a whirling. If anyone has seen some of the in my forecasts, when I focus on the activity of a particular sunspot cluster, you'll see these things. There's very, very dynamic structures. And so they're understanding that magnetism plays a role. And then they say magnetic storm sends streams of invisible electrified particles out from the sun. So they're just showing them straight out. I don't know about you, but the ball and stick method, this is not what really happens. But that's the best of their knowledge at the time. But at least they were trying to put this stuff together, okay? And in this case, we have a lot of observations of the auroral displays. And it says one of the greatest auroral displays, and this is by Craig McNish, not Craig, McNish, anyway. One of the greatest auroral displays ever observed in the central Atlantic and mid-central portions of the United States occurred on this night of September 18th to 19th. Spectacular displays from twilight until just before dawn. were observed as far south as Florida and Southern California. The auroral activity accompanied one of the most violent magnetic storms of the present sunspot cycle, equaling nearly in intensity and exceeding duration of the Great Storm of Easter Sunday. Here's another near Carrington-class event that I'm not going to cover. But yes, this storm, this one might even be on the Carrington list that Russell et al. Had. Serious interference with radio and wire communications over long distance was experienced. This is why I chose this storm, as well as noticeable effects on electric and power transmission lines. I am going to focus mainly on the broadcast stuff because it's interesting. But and we already went through the 1921 storm that talked all about GICs and the power and the railway lines and all that stuff. So let's talk about another way that geomagnetic storms can actually affect us. Okay. Just at the time of crossing the solar meridian, an increase in activity in that group, that was 7281, it was seen such active groups frequently give rise to geomagnetic storms. H.W. Wells of the Department of the Terrestrial Magnetism, Carnegie Institution of Washington, had warned numerous radio operators to be on the lookout for disturbances in the radio transmission conditions so that the occurrence of the storm was not entirely unexpected by scientists, although its intensity and the extent of the auroral manifestations were not anticipated. So hey, space weather forecasting. Wow, look at that. Before even the stand-up of the Space Weather Prediction Center, there were scientists who were actually being able to forecast and tell radio operators, look out, we might have something coming. Isn't that cool? So the storm began at 11 p.m. on Eastern Standard Time on September 17th, and it maximized between 1 and 3 p.m. and 7 and 10 p.m. on September 18th. 1 and 3 p.m. and then 7 and... This might be because there were 2 CMEs, okay? Not just 1, but 2. Again, with big geomagnetic storms, this is oftentimes what happens. When you have ones that impact us at the Carrington class level, it's typically not because it's just one storm. Even the 1859 event was not one coronal mass ejection headed toward Earth. It was several, okay? And it's just the sustained bombardment that ends up causing the types of impacts that we have. Okay, during the peak, the effects were noted on the 230 kilovolt interconnecting hydroelectric line, interconnecting line tying the power system of Washington, D.C. into the hydroelectric developments along the Susquehanna River in Pennsylvania. Did I say that right? Susquehanna River in Pennsylvania, approximately 100 miles to the north. And the second period of disturbance was when the auroral activity peaked. Okay, so again, when you start seeing, and here we'll talk about Great Red Aurora, if I recall, that subsequent activity as it continues to get lengthen, right? You're pumping up that ring current, right? You pump up that ring current, you're going to start seeing that stable red aurora arc. Okay, not a subaurora, but red aurora arc, stable red aurora, and that definitely is a sign that that ring current is really bumped up. And of course, it's going to be lower than that auroral oval typically. All right. Changes in horizontal magnetic intensity at the U.S. Coast and Geodetic Survey Observatory in Maryland accounted to over 2,500 gammas. That's nanotesla. It's an old way of saying nanotesla. 2,500 nanotesla, which is approximately 15% of the normal value at that station, the greatest change ever recorded there. Okay, so this storm was shorter in duration than the 1921 railway storm, but possibly more intense, at least in that local area. Okay. Now, the interesting thing about the playoff storm is that it ranks high in magnetic intensity, but not super high in terms of, this was the, which paper is this? Is this the Russell paper? I forget which paper this is. My apologies. But you can see it here, right? And we're talking about, remember I talked about magnetic intensity and direction, right? You have the D component, the H component, the Z component. The H component goes east-west. The D component is also horizontal, but it goes north. It goes, I think, north-south. And then the Z component is the vertical, okay? We care most about the H component. And if you look at this, obviously, if you're going to see an arrow greater than, that's probably because they're off scale. So some of the most intense, they're talking about from the intensity, right? I took the right table, didn't I? Yeah, in order of date, or oh, maybe I didn't. Oh, bummer. I didn't. I thought this was the table that had it ordered in terms of the strongest magnetic intensity. But as you can see, it's sitting here at 1250. That's pretty strong, right? Not the strongest. You can see the 1941 event, the March event, that's of the same year, which I debated doing, because that's the Easter storm that they had just prior to it. I debated doing that storm, but decided not to. It was stronger in the H component, right? But the 1250 is reasonably strong. It's stronger than some that are up here. It's stronger than the 1909 or 1903 event. Stronger than, let's see, what's another big one that you guys might know? It's stronger than the, well, we don't know if it was stronger than the railway event because it went off scale. Right, in 1921, they didn't have magnetometers in many places that would read that high. So we don't know, but it's in there, right? But here's the interesting thing, is that when Svalgaard, Cliver, and Ling did a reanalysis, what they wanted to do is they wanted to take an index that was similar. They called it AAM. Now, the AA index is very similar to the KP index. And the KP index, if you average it over a day, essentially, you take the peak amount, you average it over a day, you get the A index, okay? If you take that index and you're looking at just the peak levels over the course of the day, you're able to pick out storms that are high intensity that are sustained. In other words, high levels in the A index they favor intense, lengthy storms, as opposed to storms that could be intense but short. Okay, so that's how that worked. And these guys decided they wanted to do something very similar, but they wanted to do that, make that same kind of analysis with the AA index. So they created something called AAM. That's based on the AA index, but which has the universal time variation of the AM index. So this allows the construction of a list of outstanding storms for the period of 1868 to 1998. Get through all that, where they are able to rank order the storms according to the strength and the intensity, but also favor longer duration storms, okay? So that's kind of what they were doing. And when they re-ranked it, this kind of blew me away. 1941 ended up being the first. Now, probably not because it was the strongest the longest in duration, but because its intensity was actually even higher than even the railway event. It just didn't last as long. The peak value, right? We were talking about the dip in value, right? When we looked at the magnetometer dip at Samoa. Okay, so for example, the peak value for the May 1921 event, according to this index, and the AA index is, and I'm not going to go into it, but you can look at it in the E course series, right? When I do the ground event stuff, the AA index has only got a couple stations, I think it's only 2 stations. It's either 2 or 4. I think it's 2. It's a station in the northern hemisphere and a station in the southern hemisphere. And the reason why we have those, why we keep using that index, is because it has the longest baseline over, the longest period of time into the 1800s, like 1820 something, I don't remember when it started, 1868, 1828, something like that. So we always have that, we always use that index so that it continues over the long haul, so that we can continue on a, comparing apples to apples and oranges to oranges. If you have measurements of storms on the AA index back in the 1800s, and you have measures of storms in the 2000s on the AA index, you can compare them directly. So that's why they're using that AA index. Are there better indices to use today? Sure, but we can't make the comparisons with historical events and line them up. So that's why they use this particular index. That's why they're not measuring in Samoa, let's say. They're just, I'm thinking of the latitude of those indices. They're not much higher than Samoa. But at any rate, from that reanalysis, they're finding that at least for the period of time that the storm was occurring, it had a bigger intensity than the 1921 event. And it's funny because look was number 3, 1989, the March storm, okay, which we'll be going over maybe in our next course. But this was not a Carrington-class event, but it sure wreaked havoc. This is the one where the Hydro-Quebec grid failed, right? As you continue going down, where is the 1859 storm? I don't see it for some reason. Where are you? It's not on the list. That's why I don't see it. Am I wrong? Anybody see it on the list? I sure don't see it on the list. So the 1859, and that makes sense. The 1859 event, it was strong. There was no doubt it was strong, but it had a stronger radiation storm. I think that was one of the big things of it, right? The reason why the 1859 event is called the Carrington-class event is not just because Richard Carrington saw it, but the reason why it's such a standout is because it was bad in pretty much every category, whereas most of these other storms only had one aspect that made them really, really intense, right? And in case of like this storm, it was literally just the geomagnetic hit, okay? The 1972 event was intense, as you can see, but it was down here. Why? Why was this such a Carrington-class event? Why was it so high? This is the fastest event on record. Okay? It hit Earth super, super fast. But its magnetic field orientation was the wrong way, so it didn't create a long-duration, high-intensity geomagnetic storm. The 1941 event did. Okay? And so what you're about to see is that because this storm was so intense, even though it didn't last as long as a railway storm, we had GICs, granted, we had lots of problems, but this storm actually caused radio disruptions that were insane. They caused radio disruptions that were similar to what you'd expect from a flare. If you remember 1967, all of those radio disruptions, that was because of the radio bursts from the solar flare, okay? This is radio disruptions in the HF band from a solar storm, from a ICME, okay, from a geomagnetic storm that the Earth was creating. So the Earth's response to the ICME hitting it caused the radio disruptions this time. It's mind-boggling. And the thing is that unlike a solar flare with a radio burst, those lost hours maybe, okay, minutes, hours at worst. When you have a geomagnetic storm, it can last days, as we just talked about, right? The 1921 railway storm. It lasts days. And so now imagine having an intense geomagnetic storm that's so intense that the radio impacts last not minutes, not hours, but days. I mean, that blew my mind and that was why I liked this storm, okay? Because it shows what a geomagnetic storm can do. Both the railway storm and this one show two different aspects of what a geomagnetic storm can do if it's strong enough. All right. So again, looking, and this is kind of what I was saying, I probably should have jumped ahead to this, because there's no single definition for a Carrington-class event, right? Because look where this storm ranks on the Chris Russell side, right? It ranks clear down here, but it says geomagnetic storm. And they consider the winners, who takes the gold medal, right, for geomagnetic storms, the March 89 and the 1941 event. Well, now according to Svalgaard et al., it's actually the 1989 event really isn't even as good as the 1921 event. But that's because we're looking at storms in terms of intensity and duration. Okay? The 1921 event was insane in terms of its duration. Okay. The 1859 event, yep, it was the solar energetic particles. It took the gold in radiation storm. So hopefully with all of this, you're beginning to see how hard it is to define a Carrington-class event. It's unbelievably tough, because not only do you have all these parameters that come from the actual event itself, from the solar phenomenon that are occurring itself, but now you got to factor in how Earth responds to it, right? Which is a whole other bag of worms. So it's unbelievably tough and extremely unpredictable. Okay? This is why space weather is so tough. It's not just a one-body problem. It's a two-body problem, so to speak, because you've got the sun and all its weirdness and everything it does that we can't really predict very well. And then you've got Earth's reaction to all of its weirdness and everything it does, and which we're not very good at either. All right. Yeah, and that's just kind of what I was going into. So I'm just saying the reason why the 1859 event stands alone is because it was bad in every category. Right, so yeah, so that's kind of what that's saying. So I'll fast forward through this. Okay, now here's Jeff Love again. Don't you love it? Jeff Love is doing the geomagnetic blitz. So whoever had said the geomagnetic blitz, you were spot on. So I kind of butchered that paper and to try to kind of put things into a little bit more, kind of the way I wanted to organize things. So we're going to start with lights off over the East Coast. A lot of this had to do, remember, this is wartime, right? And people were very, very tense and very concerned. It says confusion rippled across the East Coast as the lights danced in the sky. So we're already talking about the storm occurring, and people were thinking about, German U-boats. Is the war breaking out? Are bombs being dropped on us? What's going on? Because they knew that the warboats were, the U-boats were in the Atlantic, right? The German submarines were in the Atlantic, and they could fire rockets and all that kind of stuff. So authorities during the time when Aurora was all in the skies, the authorities were getting questions like, are Germans attacking? Has it been sighted? What's going on? Is this anti-aircraft stuff? What's happening? Whoops, I should continue standing here. And it said more than 100 calls per hour flooded the Hayden Planetarium in New York City, as well as the Weather Bureau. They received so many inquiries that they switched calls to a record player that's saying the lights now visible are an unusual display of the Aurora Borealis. I can't imagine having a record player having to play that over and over again. How does that even work in 1941? When did we come up with like the voicemail thing, right? That's 70s or something with cassette tapes. I never knew that they actually could do this with phones with record players. So tells you something. Here's that picture, that same picture here that kind of gets cut off. This is the glow over Manhattan. So, it's a black and white photo. Obviously, in 1941, the cameras weren't all that great, but you can see the aurora is as bright as the city lights, right? The background is a Hudson River in New Jersey. Okay, so very, very intense lights. And, it's kind of hard to tell, but this looks like a curtain, right? This is definitely, and maybe you're seeing pillars. Kind of hard to tell. So could there have been coronas over the city? Absolutely. So here's where it's interesting. As the auroras dance through the night sky and voltage, were surging in the power lines and all that kind of stuff, the radio blackouts started occurring. Now, these aren't radio blackouts necessarily from big solar flares on the sun. These are because you've got the auroral oval, you've got aurora, literally creating problems for skywave propagation. The radio blackout caused the announcement of a baseball game to be interrupted, completely cut off, and people who were listening to the radio or to the baseball game started hearing private phone conversations. And it said that people were worrying, once again, if things were being jammed, if there were anti-aircraft or something like this, and so they were getting their signals crossed and, having a hard time tuning in the radio because of this, they were getting nothing but interference. So they were thinking that maybe there are war aircraft coming overhead and trying to jam their radios, AM radios likely. The Pittsburgh Pirates and the Brooklyn Dodgers, that was a big game that was being broadcast at the time, and it was completely blacked out. But so people couldn't get it at all through the entire game. How long do baseball games last? 4 hours? Sometimes. Long time, right? Baseball games are slow. And I think even back then they were probably pretty slow. But that didn't matter because even the next morning, right, after the night before, the radio station, here's an example of a radio station, WAAT, was broadcasting a portion of Bing Crosby, or a program of Bing Crosby. Suddenly, during the where the blue of the night meets the gold of the day, a phone conversation between two men discussing their previous night's dates could be heard in the background. So you're hearing all of this going on with Bing Crosby. Workers at the radio station tried without success to clear up what was apparently some sort of mix-up of signals. They're getting crosstalk. They're getting, frequencies are shifting. Station representatives later claimed that although the conversation was strong, it was also not objectionable, so that's fine. But that faded, and it ended up becoming a conversation with a set of girls over telephone lines. I'm not even sure how this happened. But the girls, the two young women, started talking about a blind date. And the full quote, and this was not in the Blitz paper, it was in a different paper, a different article I read. It says, quote, "I fixed it for Eddie to pick up a guy for you, and afterwards we'll go to the party," one girl said. The other one, it says, "I guess it's okay," the other replied, "but how do I know the guy Eddie is bringing for me is all right?" So people actually wrote this stuff down, right? Shortwave radio transmissions were knocked out for a while. England lost contact with Australia. Signals from Rome, Berlin, and Moscow were lost. Teletype machines like those in the Beacon Journal office, they began to print gibberish. So this was actually an article from the Beacon Journal. There were a couple people who were actually still alive who were talking about this. And the writer of the article was able to interview them. Fun stuff, right? But it tells you the level of intensity this geomagnetic storm must have had in order to literally cause disruptions in frequencies, and having enough magnetic disturbance to cause, I don't know, telephone lines, because I'm not familiar with how telephones lines were being broadcast back then. I would literally have to go into the technology of the day to try to figure out how you can get a radio station and telephone lines being crossed like that. But obviously it was happening, right? Again, as far as impacts for wartime tension, if you have aurora that bright, it's going to light up the night like people send flares in the sky, right? To be able to light up in wartime, in combat theater, to be able to light up the night sky to try to see where the enemy is. And so if you have aurora doing that exact thing for you, maybe it's going to light up things that you don't want them to light up. Yeah, well, that actually happened. So in the Atlantic, okay, there were German U-boats patrolling off of the coast of Iceland, I believe it was, because let's see, it's the Canadian and American forces. They had convoys. It's out of reach Iceland based Royal Air Force maritime patrols in search of eastbound ships that were keeping Britain supplied during the war. So we had American and Canadian convoys that were crossing the Atlantic to try to supply Britain, and they were doing it under the cover of night, right? And they had these convoys as well as these what do they call them, corvettes, that were trying to, the smaller, faster boats that were trying to keep the convoys, protected. So it says as the sun set, right, the fog lifted, but usually a convoy would be pretty well shrouded. But because of the aurora, there was a German who actually wrote it down in his log. This gentleman named Kentrat. You see it right there. It says Kentrat described the conditions as being as bright as day. So ironically, in a post-war interview, a crewman on board a ship in the convoy, in the Canadian-American convoy, said the SC-44 Corvette, that's one of the little boats that try to keep them protected, recalled seeing the aurora on that evening and remarking to a fellow crewman, "What a night for torpedoing." So even the guys in the corvettes that were the ones that were trying to be like the guides to try to keep be on the lookout for any enemy craft, were saying, "Oh God, we're sitting ducks out here." Right. And it said this bit of dark humor would turn out to be prophetic, because in the North Atlantic, it exposed us, it sure enough exposed the Allied convoy to German attack. At 22:30, Kenrat issued a radio dispatch to his headquarters in Germany, right? And the other Brandenburg U-boats, Alpha, Alpha, envoy convoy in sight. Quadrant, he says 80, 97, 61. Course northeast, moderate speed, U-74. Unsure whether his compatriots received his message, he recorded in his diary that since at 4:30 UT on the 18th of September, quote, shortwave radio reception has been very poor and it gradually cuts out altogether. We will try absolutely everything we try absolutely everything but without success. I hope the other Brandenburg boats can receive me. So, luckily for the convoy, he was the only boat. None of the other U-boats were able to get the message. Otherwise, they would have all hurried over to this location. And while this was happening, the Royal Air Force was using the Aurora from the Aurora lights to pound positions in Norway and France. Okay, and that was happening at the same time. So the Allied forces were also using the Aurora as like flares, while in this case, Kentrat, who, as you're about to find out, actually did end up succeeding. He said, he recorded in the evening in his war diary, he said, September 18th, 1941, visibility 4 to 6 nautical miles, a number of smoke plumes on the horizon, vessels seem well strung out. That's when he identified the convoy. Kentrat had spotted the convoy of cargo ships. For protection, a destroyer and a small anti-submarine warships known as corvettes were escorting the SC-44 on its journey. But at 0100, on the 19th of September, Kentrat tried several times to maneuver U-74, his boat, his submarine, into attack position on the starboard side of the convoy, only to be driven off each time by the SC-44's defending corvettes. They didn't pursue for long, but Kentrat became concerned that his own U-boat was too visible in these conditions, meaning he was being lit up by the Aurora. So, because in those days, as this thing actually says, they didn't, the submarines, I've seen old footage of them. Why submarines did not submerge very often back then, I don't really know. Probably something to do with their make or just not, I don't know. But I saw submarines would travel like surface boats, which seems kind of odd to me. They'd only dive at certain times. Now, they're almost always underwater. But then he decided to maneuver to the port side of the convoy, where the northern lights were less bright. So as he maneuvered around, they ended up obviously not seeing him. This was the boat that went down, killing 18 people. This was like if I go back, yeah, you can see it here. This is 1941, just before it sank. So this is a Canadian boat. And so he was able to kill 18 people by maneuvering away from the northern lights where it was less bright. So there was a lot, strangely enough, that because the Aurora, in this case, the Aurora lights were so incredibly bright with this one, so much more intense. Now again, this storm didn't last as long, but because it was more intense than the 1921 event, the Aurora brightened very quickly and came, and as you see from this, excuse me, this is all happening at pretty high latitudes. This isn't happening down at the equator. This is around Iceland, right? Going from Canada to Britain, right across the Atlantic. So the Aurora was extremely bright, but it didn't come down quite as far south. Here's multiple pictures, and of course in 1941 we had more cameras out, so there's more record of it, right? So here is Broomfield, New Jersey. You're seeing major curtains, if not almost coronas, and then here's even some in, where is this? Mason City, Iowa, right? Again, very bright, right? And then if you go to the Akron Beacon Journal, Akron, Ohio, it says, granted, it's not as impressive as in black and white, but here's how the northern lights look over Akron. Imagine the night sky awash in green, yellow, blue, purple, pink, and silver. So rainbow aurora, right? All of it. And so as you're seeing that obviously means that we had lots of energy penetrating all the way deep down so that you can get all of the really intense aurora colors instead of just a green or just a green and a red. You're getting, all of it. In this case, let's see what I wanted to say about this particular one. Okay, so yeah, people thought Judgment Day was at hand, of course. This is even in 1941. This is in Akron. in Ohio. So they were interviewing people, the Beacon Journal was. And it says, when blazing streamers of light turned the heavens into flame, more than one call was received by police, newspaper offices, and other central points of persons who interpreted the aurora borealis display as a religious omen. Others who did know or accept the natural explanation called to ask if the flaring banners were a new type of death ray or some other imaginative death-dealing weapon. Well, we have conspiracy theorists even back then, right? Tinfoil hat wearers. People who thought it was a local phenomenon were mistaken. The lights were visible in the United States as far south as Florida and Alabama, and went as far west as Colorado and New Mexico. So obviously not as intense, in terms of lasting, because that auroral oval, as you've seen with some of the big storms we've had recently, last couple years, that auroral oval has to come all the way down to the equator, but it takes a while for that to happen. And if the storm doesn't last long enough, it's not going to come all the way down. So this was an intense storm, but it just didn't last long enough to get that aurora to come all the way down. And then Aquan astronomer talked about the beautiful lights all night. Then he went the next day after he watched the lights. He knew there had to be sunspot regions on the sun. So when he looked in his telescope, he said there were a dozen big spots and some 40 or 50 small ones. He says, and they remained there until Sunday morning when they gradually began to slide over to the sun's edge. So as this sounds like this set of region, or this cluster, region 7281, this, remember, was part of a recurrent series. So this is one that had survived its far side passage and was back Earthside. And it looks like it was going back around again because it was surviving even another passage to potentially come back, but it didn't come back nearly as strong. So this was a set of regions that grew on the sun's disk, gave us some storming, but not a whole bunch, not enough to be a Carrington-class event, survived at least one passage, if not two, from that big catalog we looked at. And by the time it came around the second time, it had grown and fired off, the set of storms that were both, well, I don't know if it was the Easter storm, but no, I think it was too early because that was May. But this one in September, it fired off this particular one. And it says, it was a kind of joke, he said, when he returned home, this astronomer returned home from his Michigan fishing trip, because this happened when he was in Michigan, he said he thought he had an unusual story to tell his friends, but then he learned that the northern lights had been visible all around the northern hemisphere. So all up and down our western hemisphere, for sure. When we got back to Akron, and a bit in Europe as well, because in Europe, remember the forces, the British forces were using the aurora to fight the Germans, even on their side of the Atlantic. So he says, when we got back to Akron, talking to various people, they said, we thought the end of the world was coming. So it's stuck with him all these years. He's even done online research about the 1941 magnetic storm, which was one of the most intense ever recorded. So again, these big storms can be a lot of fun. Oh, good. These big storms can be a lot of fun in this case, right? Obviously, if you've got a war going, it's going to raise tensions, and that's a whole nother ball of wax. But even geomagnetic storms can cause more than just aurora. In the case of the 1921 storm, you had massive GICs and fires breaking out, and possibly death, as Mike Hapgood was talking about, was actually risking, people's lives could get lost. And in this case, well, it was more about radio disruptions and things, because the storm didn't last long enough to cause, significant GIC activity to the point where you're getting fires and things like that. This is why, as I said it before, you have to have sustained geomagnetic storm activity to worry about our power grids. And I don't mean sustained like 3 hours, 6 hours, 12 hours. I'm talking sustained like 24, more than that. 20, but such sustained high intensity for 24 hours, sustained high intensity 36, 48, okay? When you have sustained high activity for that long, that's when the grids get worried, okay? Going up and down over the course of 24 hours, grids can handle that, no problem, okay? So it takes not just an intense storm, but a sustained intense storm. Even this one being as intense as it was, it didn't have the impact that the 1921 storm did on our power infrastructure or telegraph infrastructure. It wasn't nearly as intense because of the GICs didn't get time to build up. But it was an extremely intense storm to the point where even it caused all these weird radio disruptions that, you know, I've never seen a storm in our recent history that could even compare to that. I didn't even know geomagnetic storms could do that when it comes to radio disruptions. I know that it does radio disruptions like the HF, you know, it can cause things to you know, to have signal fades and have you know an auroral propagation and stuff like that, and cause certain frequencies to work better than others, and cause sometimes just nothing but noise on the band, so you hear nothing at all. Sure, but the idea that you could cross signals and have wildly swinging, you know, radio stations competing with telephone, at least the technology of the shortwave back then, and telephone lines, that is pretty crazy. And over the period of time that they had it ongoing, not just for a short while, but for, you know, the night before and then the day after, to have it continuing for that period of time, that's pretty intense. So, and then of course being bright enough aurora that, you know, people end up dying because in military conflicts, because they use them as torches, right? They use them as ways of lighting up the theater. So, you know, instant daylight, right? So that's quite interesting. Okay. So what I'm going to do is I'm going to very quickly go over just a teeny tiny bit of putting this into perspective to get you to think about something, and then I'll stop because this is a really long one, but I'm glad we got through it. So let's just put some of this in perspective, okay? And this is not just perspective for these two storms. This is now talking about all the Carrington-class events. And so to do that, let's talk about the 1900s all the way up. So this is the 20th century, essentially, up to, you know, and then beyond, right? So this is why I call this 20th century and beyond. And when we talk about it, I'll stand on this side. We talk about it, obviously, the first one thing that I wanted to mention is that, just to kind of anchor you, the birth of radio astronomy, okay? So we're talking about HF and beyond, all that kind of stuff where we really started paying attention to radio signals in terms of how it affects, you know, what the noise is out there in space, right? That occurred right about here. Okay, this tells you where HF radio and just radio in general, radio signals really became paramount interest of you know, the technologically advanced world, the Western world. Notice it's at solar minimum, right? Because that's not solar radio astronomy. Solar radio astronomy occurs here, 1988 or 48, the birth of solar radio astronomy. Why? This cycle, cycle 18, was probably the most radio loud cycles of all time. Okay, we've not seen a cycle as radio loud as this. This cycle was damn close. This cycle was damn close. But this one was pretty intense. So all of this right here, we had the biggest sunspots ever recorded during this period. Okay, and that makes sense. Look at it. It's also the most number of sunspots. Look at the sunspot number in cycle 19, right? So it makes sense, okay? Where are we now? Way down here, okay? For decades, we've been way down here. Nothing close to what we've seen. Now, Carrington event, off scale, right? It's back over here at 1859, way the heck down that way, okay? 1921 railway storm, we just went over this one. Declining phase of the solar cycle, cycle 15, okay? Playoff storm, 1941, so another one we just went off it, right? So 1921 railway storm occurs before the birth of radio astronomy, okay? But prior to the birth of solar radio astronomy, okay? And remember, World War II is in here. 1967, we went over this one, right? Now this is the ascending phase of cycle 20, okay? And this is the one where we nearly went to World War II, or World War III. No, World War II, 3. Yeah. How many wars have we had? World War III. Tells you my brain is tired, right, if I can't figure that out. And then the 1972 Apollo storm, okay? That occurred on the declining phase of solar cycle 20. So here's the Carrington class events that we've gone through. Now, do you notice? This is the rise of the grand solar maximum. See that? Look at the cycles. Okay? you can imagine which way the arrow begins to tilt as we go this way, right? So I've covered Carrington class events during the rise of the grand solar maximum. Now, what does that mean in terms of society? Well, right back here, you may not be able to read it. This was the first analytical engine, the very first computer, never fully built, okay? This is Charles Babinger's invention. It was designed to solve computational and logical problems. So basically a very automated abacus, right? It was a calculator. This thing was massive, okay? All mechanical, but never fully built. And that was done in like 1901. 1942, so you see this arrow going here. Okay, so this is now after the railway storm. Okay, here is the very first set of electromechanical computers. Okay, massive, the size of buildings. Okay, the Mark I in 1942 is the first electromechanical computer using mechanical devices weighing 5 tons and using 750,000 parts, 750,000 parts, moving parts. Okay, here's the Colossus, about the same time, the electronic computer with 1,500 vacuum tubes. It helped the British crack the German codes during World War II. Okay, here. We had already had the Carrington class event storm and the 1921 railway storm and the 1941 playoff storm by the time these were created. Now, you remember the technology I talked about? Big, thick metal, not much aluminum, no plastic, no microchips, right? We're even talking about electromechanical weighing 5 tons and vacuum tubes, okay? Heavy voltages, heavy, big currents, right? These things are analog devices that can handle lots and lots of current and disruption, right? They're robust. Everything we built back then was big and robust. 1946, the ENIAC, the first electronic high-speed general-purpose computer, still using vacuum tubes. This was in 1946. We still haven't even discovered or created the field of solar radio astronomy yet. We still didn't have a clue what our sun could do. Okay, and we're in vacuum tubes still. Okay, in the 50s and 60s became the semiconductor revolution. Right. Here's the UNIVAC one, the first commercially marketed computer used to tabulate the U.S. Census. It occupied 943 cubic feet. Suddenly we've shrank these down a bit. Okay, still pretty big, right? But smaller, more manageable. We're going to start moving away from vacuum tubes and into semiconductors. Then I guess I should go back one before I do that. In this case, right in the early 1950s, we were still waiting to get, we'd now discovered solar radio astronomy, but we were not into cycle 19. For those who are, like especially ham radio operators who remember cycle 19, we still weren't in cycle 19 yet, okay? The Apple II, do you remember this? So now this is where all the innovation occurred with semiconductors and shrink, right? Smaller sizes, smaller components, plastics, aluminum, circuit boards, where things really began to move away from electromechanical and into solid state, semiconductors at least. So the Apple II, this was at the price of almost $1,300. The compact machine was one of the first massively popular personal computers. That occurred clear in like 1978, okay? Guess what? We had already had our 67 World War III storm, and we had our 1972 Apollo storm, okay? Those had occurred in cycle 20. But this revolution, moving from electromechanical vacuum tubes, big, hunky, massive systems using large voltages and large currents, and we're analog, are shifting away in this period to these smaller devices using smaller voltages, smaller currents. And now we have already passed through all 5 of our big Carrington class events. There's the rise of the grand solar maximum. So this system didn't even come out till after all of these events had occurred. When was the last big Carrington event to hit Earth? Like really hit Earth? Not clip it, but hit Earth and cause Carrington class event impacts? This one. So what now? Right? What's happening in the future? Well, laptops were invented, 1992. Wi-Fi came out, in 1996, I think. Here's the Power Mac. You guys remember the G4? Right, that came out right about 1999. How about cloud services? Amazon Cloud, guys, launched in like 2006. How about MacBook Air? It's like, was this 2008? Do any of these devices look anything, and any of these infrastructures like Wi-Fi and cloud computing look anything like this? Do they even resemble them at all? What does that mean? The question you always have as an aerospace engineer is, have you tested? Do you test as you fly? When it comes to space, you always want to test as you fly. If you do not do that, if you do not test the systems that you're building in the environments they're going to fly in, that is a certainty they will fail. It's not a matter of if, it's a matter of when. Okay. And from this perspective, if we know what the sun can do, have we tested as we've flown? Have these systems gone through the kind of rigorous testing of space weather events like these ones did? Can we honestly say we have no problem because these systems, these computers survived? So these should. Anybody believe that? So this is what I will leave you with, okay? Yeah. This is what I will leave you with, is this food for thought. Because what we're going to do in our next class is we're going to start moving away from the Carrington class events and into what the storms are of the modern era. Okay? And we will compare the storms to see what is out here. Have we had Carrington class events? Have we had anything that can compare, that we have similarities to? Maybe a few, right? 1989, maybe. 2003, maybe, right? But are they Carrington class? And then what's since then? How much more have we evolved since then? Do we have any storms that compare? And what are the effects? Do we need a Carrington class event to affect us to the degree that these Carrington class events affected us? Maybe, maybe not, right? Because as our technology gets much more downsized, using less voltages and less currents, maybe we don't need something quite this big. That's the big question. Because we have not tested as we've flown, right? Our sun is capable of far more than generations of human beings. Some people watching this show, this class, probably weren't even born by the time that we had our last Carrington class event. And so they have no experience, even in their entire lives, of what a Carrington event is. Tells you a lot, doesn't it? Mike says, it reminds me of my gateway computer with black and white milk cows on the box, Windows 98, yeah. Takes you back, doesn't it? Yeah. So this is all I have, guys. You stuck with me for, oh my gosh, 4 hours. This was maybe a record. Don't know if it's a record. My back is telling me it's a record. I'm tired. But I'm glad we got through it, because this was super important. I wanted to get to this point. And I have a lot more. I've actually made more charts. Some of the VIPs have seen this. Yeah, and know that I have a lot more. But this was a good place to stop, because this is really what we've gone over, right? And so you kind of get an idea of what the technology was and what the societal, infrastructure, how we were connected as a society, and really what these storms did and their impact at that time was still pretty significant. But things have changed so dramatically as we move into the space age, right? That it's mind-boggling. This is why scientists, space scientists, kind of sit there and say ridiculous things like, well, it would be neat if we could just flip GPS off for 24 hours and see what happens, right? No one's ever going to do that, but do we need to make scenarios when do exercises and drills of stuff like that? Well, in certain cases, yeah. I mean, why do you think the military does that? Why do you think the military does GPS, blocks GPS out and has these drills where these NOTAMs have to get sent out to the airmen, the commercial aircraft, air people, to don't fly in these zones because we're doing a military exercise where we're shutting off GPS. We're basically jamming it. They do that on purpose because they know that they have to learn to live without this stuff. And some of that may be due to enemy, causing problems, but some of that could actually be due to phenomena like what our sun is capable of giving us. So, okay. So what do you think, guys? Awesome class, Dr. Scove. I see awesome. That's great. Thank you. Coke Machine and, yeah, SRCX. I appreciate that. Hummingbird, awesome class. Thank you. Will you publish this chart? No, not right now. Maybe at the very end of things. I mean, I haven't published any of this stuff in a journal. A lot of times you guys get you get just what comes out of my brain as I'm building it. I mean, this stuff is literally hot off the press. This is why I didn't do the class yesterday. I was still working on all this stuff. Hopefully you appreciate what's gone into this. Rachel got out a lot of it too. Thanks, Chris. I appreciate it. Yeah, you know what some of these charts look like beyond this, so you know where I'm going. Let's see. If only people knew what it meant. Okay. Thank you, Dr. Scove, for your live class today. You're welcome. Try a day without a smartphone. No kidding. No kidding. Yeah, 4 hours. God bless your back. I know. Thanks. Thanks, Kathy. I appreciate it. Yeah. So anybody have any questions or comments about this? It says if the original OS, okay, so if our electronics go down, there will be mass chaos and zombies will be losing it. Yeah, tech zombies, right? Those of us who are completely tethered to our machines will be Frankensteining around because we don't know what to do without our where's my cell phone? Yeah, my internet. We'll be losing it. Yeah, you don't need Return of the Living Dead. We all will be that, right? Yeah, moon bouncing. There are a lot of people who do bounce. They still bounce HF off the moon. Randall says, epic as always. Steffi, you say, well-presented class, learned lots. Oh, thank goodness. I'm so glad, you guys. Is that rain on your roof? Yes, it's raining here in Southern California. If you let me know if you want to use my scuba gear on the live. Thank you. That's sweet. Thanks for the incredible solar session. You're very welcome. Why no super hat? What do you mean by super hat? Why am I not wearing something like that? That's a Coke. That's funny. Okay. I'm selling copies of the chart if anyone wants one. This? God, come on. All right, fine. I'll stand out of the way. There. You want it? Go ahead. Freaks, you could see the chart without my body on there just for a sec. So there you go. So, don't expect me to do that all the time, but, I've already had issues with people stealing my stuff and taking screenshots and teaching classes, but right out from under me. It's like, okay, you think you can teach this stuff? Fine, sure. Go ahead. You're not going to, how many times did I have to reference a series that I had taught, right? I referenced the E series, the M series, the Flare series, I think it was the F series. What else did I have to reference? Obviously more classes in the A series. I mean, I had to reference so many of my own courses just to be able to get you guys through this because of the huge things because of all the solar phenomena. I just saw a note that says, Chris, you left me a note in Patreon. No, let me check Patreon, by the way, so that I can answer questions that may have been missed. And excuse me if don't start the feed. Okay, Alex O'Brien, great. I love these courses. I'm so happy. Thank you, Alex. David N says, thanks for that. Heidi says, my question for the show is, can space weather affect underground? Oh, yes, it absolutely can. We'll talk more about that in a sec. Jillian says, you did amazing work for this Q&A. So interesting to see space weather study throughout history. You're very welcome. Broadcast radio, this is Chris. Broadcast radio at the time used copper wires to go from the studio to the transmitter. So that's probably how there was crosstalk during the playoff event. Hey, there, Chris, you just answered Heidi's question. And yes, you got another chance to get the slide without me in it. Yes, Chris, that's thank you. I didn't even think about that, but that's probably, I mean, that's excellent. So yes, if you have copper wires, not only, and people still have this today, when you have wires under the ground, even like cable, these guys actually recognize when there, especially in high latitudes, they recognize when there are geomagnetic storms because they get noise in their cables. Even the digital signals get messed up. So believe it or not, telecommunications companies and cable companies actually still recognize this. I've met far too many cable pullers who actually know something about space weather because of this, because it's part of their job. But yes, if you have copper wires, what's happening is as you're inducing currents into the rock, because the magnetic field of the Earth, right, it goes all the way down into the core of the Earth. So those magnetic fields are wiggling. They don't care that they're wiggling in rock. They wiggle. They just go through everything, right? Magnetic fields can easily puncture through rock. It may cause them to bend and stuff depending upon the conductivity. But the magnetic fields, they're not like electric fields. They don't stop at the surface of a conductor. They go straight through. So yes, those fields that then are also wiggling, they are wiggling underground. So as they wiggle underground, they're still causing disturbances. And so yes, that's a perfect example of how it can affect underground. I would think that as far as any type of storm or any type of space weather effect, that was probably the main, if not only way, that you're having big space weather issues. You know, then you start getting into the realm of geophysics when you start talking about underground. And then you get, of course, then everybody jumps into it and says, oh, earthquakes. And it's like, okay, yeah, you can think about it that way. But the problem is trying to quantify that stuff. There are so many forces going on in the Earth's crust and mantle that it's really hard to understand how the electromagnetic forces of the Earth's magnetic field, which is, you know, the Earth's magnetic field is only as strong as a fridge magnet, okay? Seriously, it's not that strong. What makes it so impactful is that it's a fridge magnet the size of Earth, okay? So it's not stronger than a fridge magnet, but it's just huge. So it can create lots of movement in potential over very, very long distances, which then when you add it up can create very strong potential drops and very strong currents. And yes, that can happen underground. So, so that's probably the biggest way that space weather, any type of space weather phenomena affects underground, is through its Earth's magnetic field. So, okay, hopefully that answers that for both. And thanks, Chris, again, for the copper wire and the crosstalk and being underground. That makes a heck more sense. Yes, secret out, corrosion, right. Space weather causes those induction in the lines, or any conduction that then induces the currents in the ground, and then it couples up into, let's say, the pipelines, which are connected to Earth, and then you get currents conducting through that, and that can cause corrosion. Thanks for this. I've learned a lot. You're very welcome, Andrew. Let's see. I've laid thousands of miles underground. Interesting. Yeah, and it's a big deal. And in some of these, I didn't even talk about with some of the bigger storms. If you go through Mike Hapgood's paper on the 1921 event, there were records talking about how cables were going to have to be relayed because some of the cables and whatnot had gotten damaged from the GICs. So there was definitely some digging up of underground cables and having to relay them down. Now we're much better, even with the undersea cables, we're much better with the currents in the lines themselves, but where the problems are in the repeaters. So the repeaters because they're conductors, they end up having big issues. And those are the ones that we worry about breaking if we were to have a Carrington class event today that really hurt us. So, okay. Well, the effects will bury themselves. The meek will inherit the earth. Cute. Okay. Any other questions, guys? I imagine you're all exhausted like I am. Let's see. I'd like to talk more about the magnetosphere, strength, polar shift, electromagnetic reconnection, and components. Yeah, there's, I'm thinking of doing a class on that because it's the and this is SRCX. Because of all the hoopla about Earth's magnetic field changing, and I can talk about that. It's really a matter of what everyone on Patreon wants me to do. Once I get through the Carrington class events, there's that. There's also, this is also kind of answering some of the history of space weather. That's been another one that people have asked for. So I will have a conversation with everybody on Patreon to find out what they want to have for the next set of courses. But we've got at least one more in this series, maybe two more, because we'll be talking about the events in the modern era. And there are a couple events that are pretty intense that might take a little while to get through. Okay, Steffi B, can you alert us to these classes on the YouTube community tab? Meaning you want me to actually post? Today I didn't have time to post on even Twitter or Facebook because I oftentimes let people know when I'm going live. People on Patreon know when I'm going live days before, sometimes a week in advance. And you can even just, you don't have to pay anything. You can just follow me on Patreon, and you will get alerted. I don't always have time because I'm a one-woman show, so I don't always have time to post things in other places. So I apologize for that, but I'll do my best, but no promises. Right now, Patreon is the place I do it. That will likely change over time where I'll add more, but for the moment, as long as it's still me, I'm pretty inconsistent when it comes to that, just because I run out of time, to be totally honest. Kathy, you say I watched the launching of many of the satellites. You use SolarHam to give me information. Yes, that's a good place. SolarHam is a great place. Kevin is a wonderful resource, and I support him if you can. I supported Kevin for on and off throughout the years. He's a great guy. Okay, Mike, what are you saying? Says, oh, that's sweet. That's Steffi B. Become a patron supporter and get advance notice of these courses among other things. So yeah, Mike's totally right. Okay, Secret Owl says, does the ring current induce a current and the magnetosphere? It induces a current in the magnetosphere, yes. There's lots of current systems in the magnetosphere. If you look at my M courses, my M series, you'll see all that. I talk about region 1, region 2 currents. I talk about the magnetopause current, the crosstail current. We even talk a little bit about the substorm current wedge, and of course the ring current. And these are just current systems along with particle populations in the magnetosphere. But those are the ones that are kind of get those are the main ones. I don't talk too much about boundary layers and stuff like that, just because we really are talking about effects at Earth. And so there's lots of little microclimates inside the Earth's magnetic system, but the ones that really affect Earth and cause things and are things that we can register easily at the ground using indices, those are the things I go over in the M series. And you learn more about that too in the E series, because that's when I go into the indices that allow us to actually kind of measure and take stock of what the current systems are doing, because it all maps to the ground, kind of like the way I talked a little bit earlier today. Okay. Andrew, she had me at magnetic buoyancy. Cute. Okay. Pete says, I don't want to miss the next class 100%. Well, then absolutely check in with Patreon. Like I said, all you have to do is just follow me. You can join, and it's not a, there's a nice way to join without having to commit anything, and you'll know. So, okay. Excellent, guys. More fiber optic now. Yeah, that's true. Fiber optic's not good in space, but it's good down here. It definitely helps with alleviating some of the magnetic concerns. Okay. You're welcome, Wendy. You said thank you for all you do, and I'm learning a lot from you, so thank you. You're very welcome. Okay. So, are you familiar with Purple Dawn? This is Coke Machine. If you're asking me, no, I'm not. I'm not. But if that's the if that's the kind of aurora that lights up at the top with the nitrogen, yeah, there's some scattered light effects that blend with typical aurora effects, and it creates a very neat color of the aurora that's pretty rare. Okay. Wow. You guys are talking amongst yourselves. Okay. Thanks, guys. I think that looks. Oh, Antonio has one other question. How is the Earth's global electric circuit affected? Again, and climate. Climate science is hard. I'm definitely not getting into that. That's not something you can ask in a particular, simple question. That's very, very complicated. And electric and magnetic fields are the right hand and the left hand. They're always shaking hands. They're always part and parcel of the same phenomenon. So you can look at the Earth's system in terms of electric fields, or you can look at it in terms of magnetic fields. I prefer to look at it in terms of magnetic fields because they're stable, right? They're constantly there. They're, like I said, they're a slinky, and they order things very, very well. Electric fields are transient and they move quickly, and there are a lot of them that aren't stable at all, and they oscillate very incredibly quickly. And it's not always easy to see what's going on with the phenomena when it comes to electric fields. Magnetic fields, though, you can't destroy. There are no monopoles. You can't destroy or create or destroy it. You can peel flux back and move things around, but they're still always there. So it's for me, it's a lot more intuitive to look at magnetic fields. But the electric currents and the magnetic field, they go hand in hand. So when I'm talking about the Earth's magnetic system, I'm talking about electric currents too. Okay, it's all, like I said, it's all part and parcel. Okay. Let's see. The Orb did a song called Purple Dawn. Cute. Okay, guys. I'm trying to see if there's any other questions. Here's Tom saying, imagine being a railroad telegrapher in 1921 when that solar storm hit and your telegraph started sparking. What a shock that would have been in more ways than one. No kidding. Especially when you looked at the type of people that were there, and what they had no idea of this kind of anything that could do this. It would probably seem magical, like some demonic, supernatural force was attacking them. I agree. It would have just been frightening as all get out. A slinky, fun for a girl and a boy. Funny. It requires electricity to form a magnetic field. Actually, you don't. You don't. You can have dipole, look at a standing magnet, right? Look at a magnet on your fridge. There's no electricity there. There's nothing flowing. There's no current flowing. But it's a magnet, right? So you don't have to have an electromagnet. Magnetic fields stand on their own. Where currents are induced is if that magnetic field wiggles. That's when you get currents, okay, or potential, depending upon whether you can close the circuit or not. So electricity doesn't have to flow in order for a magnet to form. One is not the cause of the other. Sorry, they both affect each other, okay? People who try to say, no, electric fields are where it's at, magnetic fields don't exist without electricity, you're wrong. You're flat out wrong. So stop trying to demean one and say one stands above the other. It's not true. They're both important facets of electromagnetism, okay? They just operate in a different way. And I've been trained to look at magnetism because of the fact that it's structural and it's stable and it doesn't wiggle so much. So you have a ghost of a chance of measuring it. Electric fields are insanely difficult to measure. So people who want to, especially for us in space, if you want to do measurements that you have a ghost of a chance of understanding, like the magnetic slinkies, right, the CMEs that are coming out, you want to have an understanding of their structure, you're going to be looking at the magnetic fields. You try to look at the waves and the electric fields that are inside a CME, good Lord, good night, go home. It's impossible. There are so many different waves and perturbations with the electric field inside of an ICME. It's hard to, you can't even make heads or tails of it, okay? So when it comes to space plasmas and things like that and the Earth's magnetic system, the magnetic field orders things in a way that makes it more comprehensible. Electric field does not. Electric fields flow. Magnetic fields order and lock things in. So it's a fundamentally different way of looking at things. It's a B dot V paradigm versus a E dot J paradigm, if you want to do it in terms of physics. And I prefer the B dot V paradigm because it's far more architectural. And I can see things. I can see the way the currents are going to flow based on what the magnetic field looks like. Okay? I can't see what the magnetic field looks like based on the way the currents are flowing. Sometimes I can if the currents are super stable, but there are a lot of transient currents out there that aren't stable at all. And so how am I going to get a feel for what the magnetic field is doing? I just don't. So that's why, okay? But don't try to promote one type of field above the other. You do that to your detriment, okay? You do that to the detriment of physics and your physical understanding of things. So be very careful. Okay. Anyway, I'll get off my soapbox now. Okay. Magnetic field keeps electric currents confined. Very true. Okay. You are awesome, Dr. Scove. Many, many thanks for another great presentation. You're very welcome. And yes, thank you to Mike Richardson who hung in this entire time. My goodness, this was huge. This was a massive course. So thanks, Mike. My hat's off to you, and hats off to all of you who stayed for the entire duration. I am going to go lay down now. Rest. Okay. All right, guys. Have a good Sunday afternoon or evening, wherever, or Monday morning if that's where you are now. And take care, and we'll see you next time.